All of the answers in the world are right there at your fingertips. People can't question anything anymore. And I get a bit emotional about this because it drives me crazy as a questioner. I'm a natural questioner. We need more innovators.
After a quarter century of working with private and corporate wildlife management programs across the country, I've seen what truly works and what doesn't. I'm Jason Snavely, certified wildlife biologist and private wildlife consultant. I'm sharing more than 25 years of experience through this podcast. My knowledge of wildlife ecology and management allows me to sort through the propaganda and report only the facts. My work places priority on the legacy of the land, the legacy of the private American landowner, and ultimately the future of thriving wildlife populations and the habitats they rely on.
Nine most terrifying words in the English language are, "I'm from the government and I'm here to help."
This intro may come off as a little harsh towards many of my fellow license-buying hunters, but I'd like to think of it as more of a wake-up call and a redirection of how we view the chronic wasting disease debacle. I've waited long enough, frustratingly watching the game being played from the sidelines for about 25 years. My professors and mentors really struggled with the concept of CWD in the late 90s, and they still struggle with it today. The fact is, there are absolutely zero experts on CWD in the wildlife world. The experts that popular podcasts such as the Meat Eater podcast present to you under the episode titles The Truth About CWD, they're not experts in disease at all. No, Mr. Grant Woods is not an expert. In fact, based on how he talks and his language, he's never actually read the data from any side of the discussion. If he has, he doesn't understand it. And no, the state agency biologists are not CWD experts, regardless of what state you're paying attention to. In fact, I'm disgusted with the approach of so many of my colleagues. In the name of science, whether you agree with me or not, I welcome open discussion, perhaps debate, if you prefer. I recorded this podcast with a guest and friend who really didn't beg to get thrown back into the spotlight after so many years. In fact, she's never done such a podcast. She's too busy actually doing research on TSEs like CWD in her own lab at Yale University. The fact is, many of these self-appointed CWD experts refuse to come on my podcast. The lead investigators of the Arkansas UGA study expressed that they would only come on the podcast if I provide every question I plan to ask ahead of time. They noted that this was in the name of transparency. I personally think it's unethical, unscientific, and unfair to you, my listeners. Additionally, an important part of moving science forward is defending your work. Do you see the irony here? Much of the CWD research is just junk science, and you're seeing the lack of progress with CWD management on the ground. If whitetails had a team of high-profile lawyers, what case would they be making right now as the chronic wasting disease debacle continues? Our episode titled CWD, The Rest of the Story, on the Prion Theory and Dr. Stanley Prusiner introduced an awful lot of questions about the politics and lack of credibility that the Prusiner cabal brings to the table. State and federal agencies and their nonprofit but profitable lobbying partners exclude a massive amount of very good science that show that the data supporting Prusiner's Prion Theory, the theory that many of you accept as fact, was never replicated outside of Prusiner's own lab and outside of his scientific crony network. That's not science as I learned it at Mississippi State University. In contrast, one lab, led by my friend Dr. Laura Manuelidis, has done some fantastic work that flips Prusiner's Prion Theory on its head. Why haven't you heard about Laura? Why don't these wildlife experts you watch on YouTube mention her data? Why does Prusiner's camp exclude her data and that from her colleagues from their research? That's simple. Her data don't fit their narrative. I'm here to change that and introduce you to Dr. Laura Manuelidis. Additionally, they exclude much of the research from her and her colleagues from the prion supporting papers that they publish. That's not science. No references, no citations. They avoid it like the plague. Is that science? Don't look for other podcasts who host Dr. Laura because they don't exist. In fact, this was her first podcast appearance. Why? You might ask yourself. Imagine for a moment that you've worked your entire career at a reputable university such as Yale, as Laura has. But the money and the politics support your Nobel Prize winning opponent. My colleagues have put the search for the infectious agent to bed. After fighting politics, male ego, and big money your entire career, would you really invest any more precious time elevating your blood pressure to fight a fight that you won't win? There are better things to do with your time, like actually study infectivity. I don't blame Dr. Laura for putting her time in at her own lab and for focusing on actual research. I blame us. I blame the scientists who lack the guts to entertain the data that her reputable lab churned out for decades. I blame the universities who never presented this side of the puzzle to their up-and-coming wildlife professionals like I once was. I also blame the general public, sportsmen, and hunters for their unwillingness to fight for the most popular big game animal in America. Hundreds of thousands of healthy, non-symptomatic white-tailed deer have died and will continue to die because of their mismanagement. And we're all to blame, unless we fight for the big game animal that has afforded us so many enjoyable moments in the field. Because of the white-tailed deer, I and millions of other licensed buying sportsmen have spent countless hours and days afield with our great-grandfathers, grandfathers, fathers, mothers, brothers, sisters, cousins, and great hunting buddies. Why are so many allowing this to happen without a fight? To be honest, the licensed buying sportsmen disappoint me the most. After all, just because a state agency issues tags doesn't mean that hunters are required to kill those animals. The fact is, many of my fellow hunters are obedient foot soldiers. They're unable to make their own decisions about what's best for the sustainable management of the resource that we all enjoy. Many of my neighbors will kill the very last deer or wild turkey and then blame the Pennsylvania Game Commission for it. This is insanity. Like the rest of Americans, they're only concerned with taking something that benefits them. They're filling the freezer. Wake up, hunters. You're a big part of the problem. As a wildlife professional myself, I'll admit that we need to be asking better questions. We've gotten so wrapped up in the political discussions that we're failing to allow science to science on. What is science anymore? Regardless of how old the experiments and resulting data are, we need to be reading it. When will we read the papers and look at the data from the 60s, 70s, 80s, and 90s to determine where we went wrong? What are we missing? One whitetail-focused nonprofit organization recently snapped out on social media against a rightfully frustrated group of CWD questioners. This nonprofit that makes its living off of white-tailed deer and that pays multiple salaries, funds big, beautiful buildings and administrative expenses, and enjoys a sizable expense account, claims that most hunters fully support and appreciate their state agency's management of CWD. Is that true? Even if it were true, does that mean that those state agencies are in fact making the right decisions about how to respond to and manage CWD? Or are the license buying hunters and the general public falling prey to science lacking, politically motivated educational campaigns? After all, the majority of the information or misinformation that the public consumes is presented by state agencies and their lobbying partners. This podcast is, in part, supported by the Drop-Tine Seed Company. If you like the work that we're doing, check out droptineseed.com. The Drop-Tine Seed Company is not a middleman. They, in fact, demand full transparency while working directly with American farmers and growers, real people. The primary focus is on fresh seed, wild health, and nutrient density. Seeds are produced regeneratively with regenerative farming practices to ensure clean, toxin-free seeds and plants for your deer and other wildlife. Seeds grown strictly for yield in conventional agricultural systems are full of toxins and lack nutrient density. The reload blends from the Drop-Tine Seed Company have been scientifically proven to efficiently transport immune system fighting nutrients and plant secondary compounds directly to your wildlife. Visit droptineseed.com to order your seed today. One major question I'd like to ask, and this one seems to evade even the most popular academics and researchers out there right now. Are we sure we've isolated the true infectious agent? Is Prusiner's prion truly the infectious agent that causes infection that results in chronic wasting disease? Some, including myself, ask if Prusiner's purported infectious prion even exists. You know what the news is. Do you have any idea what the rest of the story is? Whether you believe Prusiner's prions exist or whether they're truly infectious or not, have you heard all of the facts from both sides? Did you even know that there was another side. I've been paying close attention to state agency biologists and nonprofit organizations that promote a specific agenda, and to be honest, they're both sloppy. As a wildlife professional and a big fan of white-tailed deer and mule deer, I'm outraged by the way we've failed the resource. I'm demanding more, and I'm not alone. Millions of concerned sportsmen are starting to ask, are state agencies and their nonprofit lobbying partners really concerned, first and foremost, about the resource that we all love, or have politics, money, and egos muddied the waters? If I was a betting man, I'd say they're going to run with the slow the spread play call until the prevalence curve naturally begins to plateau, and as it begins to show an obvious, perhaps slight downward trend, then they'll credit all of their surveillance programs, culling and targeting removal programs, carcass movement restrictions, mandatory testing, reckless and liberal bag limits, attempted urine and feeding bans, and various other poor management decisions like bullying deer farmers out of business that quite frankly lack data and common sense for the decline of the disease prevalence. They'll use their peddlers of information, their foot soldiers who consumed all of their unscientific content, to say, see, it's working. We're slowing the spread. Does this play call sound familiar? If you were paying attention at all during the COVID-19 disaster, this is what you saw. But most didn't see this. In fact, they were too busy enjoying their new work from home staycations, and so many were overdosing their own CO2 output under their masks to even recognize what was truly happening. The longer this drags on, the more likely my prediction will come true. We've already been hearing rumblings of it. Mark my words. If you're paying attention to this, you've likely heard a pile of CWD information. If you're anything like me, you have a truckload of questions, things that aren't adding up. I decided to take a deep dive into CWD over the years, and although there will always be that group who dislikes the questions that impact their professional and financial positions, I've met some fascinating people who tell me that we are in fact missing the boat on this one. We're screwing the cervids that sportsmen enjoy managing and pursuing. Mostly, we're screwing the white-tailed deer. The fact is, whitetails are a profitable resource for so many. And by the way, the free testing is not free. The additional personnel are not free. In fact, supporting them and their families is breaking the system. The fact is, the licensed buying, tax paying, productive people in America pay for that. And there are fewer and fewer of us productive, hardworking Americans each and every day. It's time we organize a group of truly concerned individuals and skillfully fight the good fight. If you didn't watch my podcast episode called CWD, The Rest of the Story, I recommend that you watch that first to fully understand the lost and forgotten history of the slow virus model, and how one man and his hired PR firm convinced my fellow scientists to abandon the scientific method that we all say we appreciate. I'm sad to say that many of the professors, graduate students, and colleagues I learned from have abandoned the scientific method for their own self-interests and for the declining U.S. fiat dollar. I find it ironic that my wildlife colleagues opted for the play call known as slow the spread when it comes to recklessly killing healthy deer, but they've abandoned the science that reveals data that show the best fit model for the infectious agent is in fact a slow virus model. To give you some perspective on that science and those data, I'd like to introduce you to my friend, Dr. Laura Manuelidis. I've gotten to know and respect Laura because her lab is, in fact, the only lab that actually studies infectivity. She's witty, she's a tough chick, and I'm proud to call her my friend. As late as this morning, Laura tells me she's still working on the TSEs as a full professor at Yale because she thinks their wonderful mystery is not yet solved. And I concur. Enjoy. Since this episode was recorded with a lifelong researcher who relies on funding in the form of NIH grants, I felt it was very important to give my guest the opportunity to review the final podcast in its entirety. After reviewing our work, Dr. Manuelidis made it very clear that her work was generously supported by the NIH, and she greatly appreciates the NIH for financially supporting her research on TSEs, including CJD, as well as her work on DNA and chromosomes. She notes that without this funding, these studies would have never been possible. I promised her I would record this for the record. So welcome, Laura.
Thanks for inviting me.
Absolutely. We've had many, many conversations about this. And how to start this has been something that I've thought about for a long time. But I keep going back to something that I wrote down during one of our first conversations. And at the time, it didn't make a lot of sense to me, but now it does. And I'm going to read it verbatim to make sure I don't misquote you. But you said, "You're extremely courageous for taking this on, Jason." And I wrote that down because I didn't think I was doing anything crazy, not in a foxhole or anything where I can die. But after speaking to you for so long at incredible lengths, and you have basically given me the equivalent of a medical degree, I understand now what you meant by that. Do you remember that?
I do. And actually, I warn people who come to my lab and people have warned me, Laura, just give up. You can't fight City Hall. That's what they say to me. And they're right in many ways. You can't fight City Hall. And this field is actually littered with people who've been great, who have been destroyed, but actually what they said was correct. The most notable of which was Wilson, D.R. Wilson, in the 90s, who first showed that you could transmit and have replicating agent in sheep. He took brain, homogenized it from one sheep, put it into another sheep, and basically it made more than a millionfold of that material and caused the disease much later. And he also showed that the agent could be filtered like a virus. He also said it was difficult to be inactivated, as by just formaldehyde. And when they're talking about inactivated, what I mean is sterilized, because actually it probably does decrease. It does decrease the infectivity, but it doesn't completely destroy it. So there's a big difference that I'm going to mention once in a while between sterilizing and basically reducing infectivity by a millionfold.
Here we
or
go.
10,000-fold.
You are an absolute, and I can say this after many, many conversations, you're brilliant. And
That's embarrassing.
whether how do I say this? Whether the people, whether it be scientists or just my listeners, regular
Right.
listeners, agree with you or not, one of the things that I'd like to point out, and we're kind of on page 7 here, getting ahead of ourselves because I want to back up a little bit here in a minute, but before we get too far into the details, what I want people to understand is, I guess, a couple of things. Number one, this has been delayed for a very long time, both prior to me actually speaking to you and finally connecting with you. And then once I met you, I thought to myself, wow, the people in my field, my colleagues, if you will regularly have who they call experts on podcasts, et cetera, in articles, and discuss chronic wasting disease. Now, obviously, we're going to discuss the TSEs in general, but CWD and Scrapie and all of these are closely related or similarly related. What bothers me most is that most of these, I'll do the air quotes, experts do not have a medical degree. They're PhDs, and that's fine. But most of them, if not all of them, really haven't done any research when it comes to transmissible spongiform encephalopathies. They maybe have done some, radiotelemetry, radiocollaring type work and prevalence work, but that's not research. That doesn't help. And the fact that we have not really made any traction in chronic wasting disease has made me, over the last 20 years, sit back and think, if I was on a road trip and I looked over at my wife and said, hey, we are very much lost, we would probably have to backtrack and say, well, at what point did we make the wrong turn? Right? And that's kind of where I met you.
So let me sort of pick up a little bit on this and first tell you that some of the greatest discoveries in these diseases were done by veterinarians. And we've had veterinarians in our lab. And I think if you ask, quote, experts, there are only a few veterinarians who are really currently working on the disease in sheep, let's say. There are many, many fewer working on the disease in deer and cervix. But the point is that the basic discoveries, the really basic discoveries, were done by people who work with animals and transmission in animals. And most people don't have that experience now. It's not a question of being an MD. It's about a question of seeing what disease really is. Look, and Hadlow was one of the best people in this field. And he's the one who looked at kuru and saw the slices of kuru. He also did brain pathology. And he said, wow, that looks a lot like Scrapie. Maybe you should transmit it. There's also a person who's a doctor who sort of smelled that it might be transmissible, and that was Jakob Creutzfeldt of Creutzfeldt-Jakob. Okay, his cases were correct, and he said maybe you should inject it in rabbits. So some of these things, and Sigurdsson in Iceland, and a lot of these people who actually work on this in veterinary contexts, many of them call it the infectious agent. And they separate that from the disease, they say, that causes a prion disease. So I know that you've asked me a lot of times, what is a prion?
Well, maybe let's stop right there, because let me back up really quick and just can you please give us, for those who don't know you, well, heck, have you ever been on a podcast like this before?
No.
Okay.
I've been on TV, PBS.
There you go. Well,
BBC,
that's far bigger than this podcast.
No, but it's different. It's a certain kind of
Well, when we first spoke,
it's not as free-spirited.
There you go. You say whatever you feel the need to say.
Right,
When we first spoke, you may remember I asked you, Laura, by the way, it's Dr. Laura Manuelidis. If I call her Laura, no disrespect, I'm just calling her Laura. You may remember me saying, how come the deer world, my world of chronic wasting disease, has not brought you into our circle? And that's something that I want to do today. And I'm blown away with your scope. You have been around far longer than this 1982.
Too long.
Well, this 1982 paper that made Prusiner, we'll get into Prusiner, famous, and then led to the 1997 Nobel Prize, which obviously, per my colleagues, I'm not looking to make enemies, but everybody thinks that chronic wasting disease has originated in 1976 or 67. And I think you'll disagree with me that a lot has happened prior to and around this Colorado positive that came up in mule deer in 1967. Beth Williams or under Beth Williams' observation. So
Wa-
can you back up before we get
Was
into
it
the
eight? When was chronic wasting disease? I thought it was 80s, early
no,
80s.
no,
It's 67, it's
yeah, so
70.
it was 67-ish that there was a mule deer in a basically a research pen
Right.
in Colorado. Yeah, and fortunately Beth Williams had identified this and had some experience. I feel like it was in Canada somewhere, seeing prion diseases or
Scrapey.
TSEs, perhaps scrapey,
Scrapey. So
and
Marsh is the person. Marsh was a person who actually, I thought, in the 60s or early 70s, hypothesized that deer or other kinds of the wasting disease, it wasn't. I thought that the real sort of focus was only really written about epidemiologically until the 80s. But you're right, I'm sure, because he said that this is probably from some scrapey brain that contaminated the deer.
interestingly, there was a solid 12 years before anybody really wrote anything about it. And
Right.
unfortunately, Beth and her husband were killed in an automobile accident. I want to say 2002-ish. Don't quote me on that. So it's sad to lose someone who was there early on.
Right.
So anyway, I'd like to back up before we get into all the details. Can you
Right.
tell us, Laura, a little bit about you, where you were born, however you feel is, whatever you feel is necessary to
So
gain our
I
trust?
was born in the center of the universe, Brooklyn, New York. They say that when I was born, they said that the huge part of population of the United States was born in Brooklyn, New York. Well, they migrated other places. So, and then we moved to Queens when I was 13 or so, and I went to a big public high school named Jamaica High School that has lots of very famous people who are great, who won Nobel Prizes, as well as athletes, very diversified, lots of talent, lots of artists, musicians, etc. And then I went to a little school and studied poetry. That was what I majored in. And I took some summer courses at Harvard, physics and etc. And I worked in the backwoods of mental hospitals during those summers also. So I got very interested in schizophrenia, to be specific. Okay. And the sort of terrible ways people were treated. Okay. In these sort of locked up in these backwards and drugged up and etc. So then I decided, I mean, I have said this before, and I think it's sort of known that I said, my brother asked me, he said he didn't see any want ads in the New York Times for poets. What was I going to do? I said, well, I'll go to medical school. And I said, if I don't get in, if I apply and I don't get in, that's okay. Then I don't have to go to medical school. And I don't know why they accepted me at Yale, I suppose, to round out their class. So I was a sort of diffident, not particularly good medical student who didn't go to class all the time or even most of the time because I didn't know what they were talking about. My friends all knew because they'd all been science majors in places like Yale and Harvard and played frisbee with me. And then eventually I went in pathology. I really fell in love with pathology. Also physiology. I had a great teacher in physiology. And that's where I really began to get interested. And pathology, studying disease, I finally got hooked. And so I actually went into pathology and was trained in pathology, then neuropathology. So I do diagnostic as well as experimental neuropathology, trying to find out what's the source of things. And I have to tell you, it's been a great life because there are tremendous things that have been discovered about diseases, about immunology, about viruses during my lifetime in science that were never known. Okay. And they continue to be discovered. So I think, and now there are all sorts of things happening in neuroscience in terms of helping people, let's say, who are paralyzed or who can't speak, etc., or move or have certain thoughts to be able to be much better.
So your email is at Yale. So did you spend the bulk of your career at Yale? And can you talk about your
Yeah,
lab
well,
and your research?
they interviewed me. Yeah, and they said, well, a lot of the schools didn't have women, so they would always ask you these terrible questions. You're going to get married and blah blah blah, which of course I was very sarcastic about, which they didn't like. So they didn't ask me that at Yale, which I thought was very nice of them. And they didn't have tests, which I thought was great because that's the way I went to school and college. We didn't have any tests. And so basically, when they interviewed me, they said, well, a lot of people stay here I said, I'll never stay here. And then my husband asked me to marry him. He was my teacher at one point. He said, will you go with me to Timbuktu? I said, we are in Timbuktu. Actually, Yale is a lovely community, especially for raising kids. It has tremendous diversified arts, sciences, music. It's just wonderful. I mean, it's a small town. It has a lot of people. People know each other. My kids went to school here, and they know a mix of people from all over the city. So that's where I stayed.
Okay. And
But
did you?
I still am in my heart a New Yorker. I will always be a New Yorker. I still don't know the names of all the streets in New Haven. I know what they look like.
Now, for how many years did you have your lab, and did you do your research, and what years are we kind of talking about here?
Okay, so I graduated from medical school in 1967, and then basically I took an internship and a residency in pathology, and then in neuropathology, and became an instructor. Then I became an assistant professor. And then I moved to another department, the Department of Surgery, because somebody didn't like the research I was doing or didn't, whatever it was. I don't know. But anyhow. And then they asked me why I didn't work with them. And I said, well, you work on red cells. Red cells are dead cells. They don't even have a nucleus. And I was interested. I was actually working a lot on on DNA and discovering certain DNA sequences like the ones at centromeres and ones called lines, which are related to retroviruses eventually and very, very early on. And then sort of looking at chromosomal structure and how cells are differentiated. And then when my husband trans me, I began to join him and do that as well. Okay. So that was in the 1970s. Both of
Okay.
the things were going on. And then basically when he died in 1992, I had to make up my mind about whether I was going to continue to be loved and work on chromosomes or whether I was going to go full time on CJD. And I suppose I figured since I'm a doctor, I could pay back a little bit by trying to do something in medicine serious. So that's where I spent my time. And it's actually, I also got fascinated by the idea of, of subliminal viruses, latent viruses, and things that we don't know about. Because a lot is known about acute viruses that like COVID. You get it and it kills you fast. Of course, you see the sequelae of it as well, which is an interesting part of this whole story. But you have a lot of hidden viruses. And, as things went on, it became very clear that we have a lot of things in our system that we don't even yet know about,
Mm.
from the environment that we probably harbor. And we harbor viruses that are usually not lethal, but they're not lethal. They sit in us and then suddenly come out of the woodwork when you get some other infection, some other stress.
This is a key point that I'd like to kind of hang on for a minute.
Okay.
I had dealt with chronic Lyme disease
Right.
and still do, I believe, whether it truly is chronic Lyme or any tick-borne or insect-borne infection. I've traveled and hunted all over North America, so I've been
Right.
bitten by ticks in Mexico and then in Canada and everywhere in between. I had studied myself intensively in how pathogens and viruses can, as you say, they can be latent or they can hide in
Right.
dormancy, if you will, for many, many
Right.
years, just waiting for an opportunity to rear their ugly heads, whether it's stress or you break your arm or you
Right.
get sick or whatever. And I remember asking you one time, I have a firm belief that the mere presence of a pathogen in our system, in our bodies, does not equate to having that disease. And one of my first tests on whether I would agree with anything you said was, Dr. Laura, if I have a certain pathogen in my body, but I'm not showing any symptoms of
Right.
the diseases that it causes, wouldn't that mean that I'm the epitome of health? Or at least until I get sick. And then essentially when I heard about your latent virus and slow virus, which I know made a lot of people mad in this prion or prion
Right.
arena, and we'll get more into the naming, and
Right.
that's a whole fun topic. I've spent way too many months learning about the history of how the prion or prion, Stan, was named, and we'll get into that later on. So anyway, I find this latent virus interesting. When I started studying your work, I first read about the Manuelidis and Stan Prusiner's 1982 science paper, which somehow has become fact. And of course, your husband was the lead author. And I read about you and finally found you. And one of the first things that fascinated me was I went to college in 97. And as you know, there was a lot going on in the prion world in 1997. My professors taught us about chronic wasting disease very much minimally. And obviously we didn't know much about it. They still don't. But we learned about the whole, prion theory.
Right.
But Laura, no one ever said, you know what, there's these contradictory beliefs too, that perhaps this is a virus. Right? They were 110% hook, line, and sinker. It's a misfolded protein called a prion, they taught us, which in hindsight, I wish I would have stuck with prion, but I keep saying
Right.
prion, and I'll explain that later. My first question was, why have we never heard of this research? I started digging into the research, met some really fascinating science writers who said, yeah, absolutely, you should be talking to Laura, and that's how I found you. So
Well, they don't talk to me anymore, so it's easy,
that's good. That's why I did.
which is very nice. But I have to tell you that, there are many people who, especially in England and Scotland, who were totally against the prion theory, as they said, oh, wait till Stan tries to explain strains with a misfolded protein, and etc. They've been ignored. They were considered, they were written off, including by some of the famous people in the prion field who supported the prion theory and et cetera. They were written off as being antediluvian, passé. We don't believe in Koch's postulates, don't apply in this case, which are
So
basic. The principles, they're principles of infection, principles of disease.
absolutely. So when you listen to or watch every podcast in my space, and I know you speak a lot about Scrapie, which is really where the initial work was
Was
sort
done.
of done, yeah,
Absolutely.
which is great because Scrapie, well, one of the very good arguments is that CWD sort of originated from Scrapie, sheep, etc., and that's a whole other topic that we'll talk about some other time. But I guess when I watch these podcasts and I listen to these experts for years, Laura, for years, it triggered me, as they now say. My
Right.
family will say, hey, you're triggered on this topic. I ignored it. I ignored it because we didn't really learn anything about it.
Right.
When I would ask my professors who I respected post-graduation, they would say, well, you better contact the Southeast Cooperative, wildlife disease folks and talk to them. And no one really understood anything about it. If you don't mind, I forget this gentleman's name, but he passed away a few years ago. And I remember he had a quote, and I've used the quote and his name in other podcasts. So hopefully some of my regular listeners remember who it was and they remind me. But he said, you don't truly understand the opposition's argument or their case until you can argue that case. So in other words, if you can sit there and say to me, or not argue, but describe in full detail what the opposition fully believes. I keep getting onto this science. Science is the pursuit of truth, right? And do we ever get there? Who knows? But during COVID, when people would say, hey, we're going to follow the science, oh boy, did it trigger me. And when this Fauci character said, I am science, I thought, oh my, did he just take something that's very important and just crumble it in his hands? And, not getting personal or political, an ignorant statement. Science is the pursuit of truth. When we were just undergraduate students, we would sit there and debate science, and some of us would look like fools, forget to cite something, mention something that really was, never truly proven, etc. And here I am watching some of these PhDs who yelled at us for making a comment that was just found in some popular magazine like Deer and Deer Hunting, and it's not science, right? And here they are now doing that same thing.
It's hearsay, and they begin to use words very loosely. But the disturbing thing is when scientists begin to use words loosely and sloppily and really don't have controlled experiments or don't have reproducible experiments. And that is really difficult, to be able to contend with. And then they say it's in the textbooks, it's repeated over and over. It's repeated, it's the mantra, this is what it is. And then if you disagree, you're attacked. You're basically attacked personally. You're not attacked on a scientific basis. So all you can do is just say, listen, there are facts. There are reproducible facts. If anybody wants to find something that we did, they can do it. These are actually some of the experiments are extremely simple, like the ones for nucleic acid. So say, as you mentioned to me, and we can get into it later, there's no nucleic acid. Well, if you refuse to do an experiment that's good, it's molecular sophistication, instead of something that's from the 1920s of nucleic acid, where you pour in some Clorox and say, well, that means it's not a nucleic acid.
Yeah.
I mean, this is not acceptable. But I think that it's really also the failure of people now, young people, to be forced to look at old literature. I can tell you, when I was in medical school, it was so long ago, it's antediluvian, that I couldn't understand the textbooks when they were talking about how the heart beats Darling's law. And my teacher, who was great, he said, who I had who I actually did my thesis with in medical school. He said, why don't you read the original paper? It's a beautiful paper. As soon as I saw the experiment and what was done and what the result was, it was very obvious. I didn't have to memorize a law or think about anything. It was very logical. It made sense.
You know,
So these are the kinds of things, and I think not reading real papers and looking at summaries and looking now at people become famous for writing reviews, and yet they've never done any of the work.
right.
But they write these big reviews, and then it's very sloppy. People then cite the reviews.
And I want to real quick. I want to make a point. I'm sorry.
Okay,
I know
sorry.
we've done this. We're both smartasses a little bit, and you and I have gone back and forth. So we've bonded quite a bit.
Right,
But I'm
right.
gonna interrupt you because I want to point something out before I forget. You have never asked me for a list of questions. You have never said, Jason, you can't ask me this, or Jason, please ask me that. We've never done that. What we have done is we've had conversations and I've said, Laura, stop. And you keep going. I said, Laura, stop. And you keep going, right? Remember this? I said, I'm not saying that we're a bunch of idiots, but the verbiage you use and, we're not all in the medical field, right? That doesn't
Right.
mean that we're dumb, because many of the listeners can probably talk about electricity or, mechanics or
Just stop
whatever.
me and ask me what a word means
Yes. No,
to
I
me.
just wanted to point out that there will be times where it gets very, very thick because you're brilliant and there's many other brilliant people. But I also want to point out that I have had people ask me, hey, yes, I'll podcast with you, Jason, but send me a list of questions that you're going to ask and I'll tell you what you can. Is that science?
Well, I think if the questions are good questions and the person answers honestly, it can be.
Yeah. And obviously, if you're not comfortable, or if I make some crazy statement like, Laura, there's no such thing as, your research is bullshit, you can certainly prove me wrong and say, Jason, no, if you actually look at this, that, I don't
So,
understand.
so I will actually tell you something. There are people, even at Yale, who won't speak to me. And then they'll tell me that I'm totally wrong. And they'll tell me, do I know colleges? I said, of course I know. I know all these people. We all come from a long time ago. And, it was a very small group of people. And I said, and they say, oh, well, you should read this paper. As I said, I know the paper very well. I know John very well. And I said, and you can't purify amyloid. That's why there's been a whole thing about making artificial amyloid to see if you can transmit an infection or get an infection. So, and I say, do you want to read some papers about that we wrote? No, I'm not interested.
Yeah.
And then I said, why are you yelling at me?
Yeah. Yeah. So you know how I
It's like,
feel.
it's like, I'm so stupid, like, how
I
can I
have
not get it?
I have amassed an incredible, stacks of papers because I'm old school. I like I have
Right,
electronic copies, but
right.
I have so many papers in my office right now. My wife wanted to drop a bomb on it, but I just sit there and I read things and I have read them all. And I've had colleagues say, I don't have time to read that shit, Jason. It's frustrating to me. And I'm not
Right.
saying this is all of them, but I was recently, for many years, I'm going to add this in here because it's important. For many years, I refused to get into the debate on CWD.
Right.
And I remember telling a good friend who is also a client, I don't like talking about it because I actually can make enemies, not by attacking anyone, but by saying, hey, let's consider this latent virus thing. This
Right.
really makes a
Right.
lot of sense. Let's revisit the nucleic acid thing. This makes a lot of sense. and they get mad at me. And I recently went to a CWD educational event in my home state of Pennsylvania. For years, I've been invited to these. Someone finally convinced me to go. And I asked friends, I asked family members, I asked local clients, do you want to go with me? And all of their responses were the same. Absolutely not. I will never go to a CWD meeting with you. So anyway, I go to this meeting as a scientist and as a landowner and a taxpayer. And I'm sitting there for 39 minutes watching a series of slides that was all opinion-based. Not a single citation, not a single reference on where these data, these graphs, all of this information came from. So to me, that's an opinion piece. In my little notepad, I jotted down 7 questions, and I had about 37. I jotted down 7. And I thought, I can't wait to ask these questions like a true scientist in front of all these great people who paused their lives to come out here tonight. At the end of the 39-minute talk, this fellow biologist who I would probably enjoy, a bird hunt or sitting by a fire pit with and smoking a cigar with. And I thought to myself, boy, this is a bunch of bullshit that these people are digesting this. I can't wait. And then the talk ended, Laura, and he said, okay, if anyone has any questions, don't ask them. Around the room, there are certain people placed, who work for the commission, et cetera. You may go ask them. And I thought, boy, now we're going to divide and conquer. This isn't science. I want to be able to ask questions. And you're not allowed to ask questions anymore as a stakeholder. So I just wanted to insert that. It's one of the things that finally lit a fire under me to say, hey, wait a minute. I'm going to introduce Laura to people. And I hope my colleagues reach out to you and say, Laura, please help us, because we're not getting anywhere with CWD, but I don't expect that they will.
Well, I think the real problem is when you have blinders for anything except your favorite molecule. And prion protein, which we used to call glycoprotein 34 because it's 34 kilodaltons. I said, that is not a mouse. That's not a deer, but it's looked at as everything. It's the disease. It's the infectious agent that causes the disease, et cetera, et cetera.
I might try to turn you up a little bit because it's not quite as loud as I'd like it. But
did you find maybe I can help you here? See if I don't want to mess you up.
It's reasonably good, but
hold on.
You're getting too relaxed in that seat back there.
How is that?
Yeah, that'd be good. That'd be perfect.
Okay, fine.
Okay, we've beat around the bush quite a while. Let's get
the meat.
Let's do that. Let's talk about. I recently had a neuropathologist say to me, Jason, well over 90% of any credible neurologist believes Stan Prusiner's prion theory. And I said,
so he's going to define a credible neurologist as somebody who, quote, believes
bingo
in a theory.
Right. But my first thought was, great, let's talk to the 10%, because the 90% could be wrong since we're not really gaining any ground here. So anyway, if you don't mind, can you talk a little bit about what they think is this misfolded protein, the prion or prion theory? Maybe I should stop saying or and just talk about the fact that when Stan Prusiner, one individual, by the way, Stan's been invited on the show. He's been invited to have conversations with me, and this is not a Stan Prusiner bashing by any means, but if you were awarded a Nobel Prize for something, I would think to the very end, you would want to, be in front of people and certainly defend what, why you won the award. So at any rate, in his one of his lovely writings, Stan mentioned sitting in San Francisco and the most beautiful scenery of the world. And he's thinking, oh my gosh, I've invented something something new. It's a novel pathogen. At one point, he called it a microbe, changed his mind, blah, blah, blah. And he says, I need a name. Actually, one of his friends said, you need a name, Stan, or somebody's going to come along and name it. It's got to be good. And he sat there eating his tuna fish on rye with extra mustard and blah, blah, blah. And he said, I'm going to call it, he went through all the proin and blah, blah, blah. And he put this infectious and protein on the X and Y axis and came up with prion. and he thought, oh crap, he looked, and here a bird is actually called prion, and or prion, I'm sorry. So blah, blah, blah. So one man, Laura, I know this bothers you because
but
you
listen,
like to stick to
I think, you're getting into this mythology and stories that have nothing to do with the disease, that have nothing to do with the facts that you really want to bring forth. And you've been diverted. And this is one of the problems. This is one of the problems with the field, because I really don't care if it's Stan or something is pronounced one way or the other. I like something to have a definition. One of my great friends, Ian Gresser, who was one of the co-discoverers of interferon, he went to a lecture by Aguzzi, and he's talking about prions and prions. And he says, what is a prion? And he says, it's the thing. Okay. So other people say it's the disease. Other people say it's the infectious agent. So all of this is however you use it. I really object to the fact that people come and they're perfectly aware of this, and they'll tell an audience, we injected prions into this animal or into a tissue culture. And I call at the end, I said, don't you really mean that you took a clarified brain homogenate? You weren't injecting prions, you were injecting a brain homogenate. And then they get flustered and they don't know what to say, because they're covering up with some of the language the actual facts of the experiments. So this is where I think it's really important not to listen to their stories. How are the words used? Are they used consistently? What are they saying? So there is a protein, 34 kilodalton protein, that's glycosylated. That's okay. It's been renamed prion protein. There is a locus where this protein is made in the host. It was discovered a long time ago by genetics, by Dickinson, doing very, very long, sophisticated genetic experiments to say where it was, and it affected the incubation time. So an animal with a change in that locus by genetically, would have a longer incubation time than another mouse. And that is a susceptibility gene that's necessary for infection. All viruses have to use something of the host. Classically, it's like a receptor. It's on the cell membrane, so it may well be a receptor that allows the agent to get a start, get a foothold, or do its thing in order to get it to be able to replicate itself with the help of the host. Okay? That's a very different story than saying it is the infectious agent. So I think we should really, at some point, say, what is the infectious agent? What are the facts? What is known and what is not known? Because there are things that are not known and there are things that are known.
Absolutely.
And again, I'm sorry for taking you away from the story of that.
No.
I couldn't care less how Stan thought of it.
I know you couldn't, but my point is, for the listener, what fascinates, and I'm not going to hang on this much longer, is the prion that he supposedly found. You had viruses, you have bacteria, you have, parasites, but all of a sudden there's a protein that has no nucleic acids, right?
But he claims it actually, it can bind nucleic acid, but so can a lot of proteins.
Right. But it just misfolds. And the only reason I'm bringing this up, Laura, is because all of the people listening to this have watched 2 or 3 podcasts, and they're all called The Truth About CWD. And when they start it with the experts, no offense to these people, they're smart people. They say, hey, this is a prion disease, right? These proteins just go rogue and they just misfold. There's no nucleic acids. It's
Dr.
crazy.
Jekyll and Mr. Hyde. That was from the Nobel Committee. We have no doubt.
Yes. So
one always has doubt.
So interestingly, in 1982, this name is made up, 81, whatever, and it's published in Science. And I just want to point this out, that one of the researchers in Prusiner's lab, you can argue with me, I've asked Stan to come on, and this is one of the things I want to ask him, because I wasn't there in the 70s or 80s. I was 4 years old in 1982. But I was told that one of the main researchers in Prusiner's lab actually quit when the publication was put out there because, and I wrote it down, he argued that Prusiner was over-interpreting the available data to push the prion hypothesis. Again, I'm not saying he or she is right.
Listen,
I'm just saying,
of course he did. It's overstated. It's way beyond what he was able to show. Okay. But it's revolutionary. And then when you find out subsequently, several years later, that it is a normal protein, he has to change the whole thing. He didn't have a folding idea. He had to adapt his theory so that he could say, well, it's folded. And he didn't find amyloid. Other people found amyloid. Kirsten Mertz first noticed it in scraping. She said it's just like Alzheimer's, but it's a little bit different in the dimensions. Okay? So there you go. And other people, actually, the people who found the protein were Bentheim and Bolton,
right.
and they made the antibodies. And it was
Okay.
a band on a gel, okay?
Okay,
In the
so
gradient.
everyone, sorry, I like pushing you until you get angry. That's kind of fun for me
Why?
because
I don't like to get angry. I
you are
just
a
want to
real
have,
scientist, and I enjoy that. So nothing personal. I just wanted people to hear that. They hear enough about all this now. Let's talk about your belief. Now, that first paper, or there's a
it's not
paper.
my belief. I don't have a
Oh, there we
belief.
go. I said it. I said it. So I was going to ask you when we started, do you remember the word that I use that triggers you? And you have yelled at me many times for using that word belief. I like just kind of ribbing a little bit. So let's get to this latent virus or slow virus, the thing that really pisses Prusiner off and his
Right.
band of Indians.
So the slow virus designation was made by Sigurdsson in Iceland. And if I may, I'm going to go back and say nobody cared about sheep diseases, but Iceland cares about sheep a lot because they make a lot of money from sheep. They live on sheep. It's a very important industry. And he said there are two different diseases, one called rider and one called scrapie, because the animals scratch themselves and excoriate themselves on the fences and rub off their hair. But their wool. I take it back. Forgive me for
We got
that.
you. We got you.
Okay. So, and the two diseases were prototyped with scrapie, which is transmissible encephalopathy, which was first transmitted serially before that uh, by D.R. Wilson and then by other people in the scrapie field in England and London, and eventually put into mice, okay, by Chandler, which is what RML scrapie is. They got it from Chandler in the UK. Okay, fine. But basically, one of them was a lentivirus, and that turned out to have a very long incubation period. And it had a lot of mutations that I'm telling you the story. So basically, the animal would respond to it, and then they would suddenly get sick again. So the virus made was actually an RNA virus, just like HIV, and it became the prototype of HIV. So you would have exacerbations and remissions, and you could have the immune system very much involved. And of course, you had to travel by the blood, not by cells, but actually in, free blood or in the lymphocytes, whatever. Okay. So then the other disease was scraping, which was slow. It took a long time when you injected it or the animals were exposed to it to get sick. So it was a latent virus. Now, anything that lives inside a cell, a virus or a bacteria, which is basically where our mitochondria come from. It was taken into us, in evolution a long time ago into mammalian cells and became what we use. We use now. We wouldn't be able to live without it. It makes energy for us. So all of that is really interesting and basically has been forgotten. And people begin what's really important when you talk about the disease for hunters, for anybody. And people in medicine, we're going to look at the early stage of disease. What they mean by that is they're going to look just before the animal gets sick and when they can find some prion protein. And then they say, oh, great, we can diagnose this because it has this abnormal protein. But actually, the infection starts much, much earlier. And it sits around and it begins to replicate. Okay, and it replicates slowly. I think it replicates slowly in an animal because the animal has an immune system and an innate immune system, meaning it's not dependent on antibodies. Antibodies can't see it when it's inside a cell. There are other viruses that live inside a cell too. And then basically, it eventually comes out and can spread to the brain. Now, there are a lot of viruses that do this. Some of them, like poliovirus, most people who got the neurological disease never had. They basically either they got no symptoms, okay, or they got gastroenteritis for a while. Lives in the environment. The kids get it in spring and summer when they're messing around with all their other friends and going to the pool, etc. And then it goes to the lymph nodes and spleen in some cases. That's a small proportion. And only very, very few people get the neurological disease. So one of the things that's interesting about TSEs is, and I don't know the answer to this, and I tried to do the experiments, and my husband wanted to do these experiments. We tried to do this with blood, but we tried to inject blood from people who were normal in different age groups to see if we could transmit a transmissible encephalopathy. And ultimately, at first, it looked like some of the animals were sick, but none of them were able to do serial transmissions. So we said there's nothing that we could detect early with this sort of crude aspect of saying, we're going to inject white blood cells from people, okay, random people. But it means that you have, if somebody really has something there and it's in the spleen or in a lymph node, if you're taking a rectal lymph node, like in CWD, it seems to me that well before even you might be able to see prion protein, if it has prion protein, it's like saying, here's the footprint. The virus was here. Okay? Not all cells make that footprint, but you could say it's definitely there. You could say this animal might be harboring a latent virus.
If I could distinguish something right there, when you say here's the footprint, this goes back to one of our many conversations. I said to you, so Laura, you're not saying that this prion protein does not exist. But what you're saying
is it's a normal host protein.
Yeah, okay.
And it becomes amyloid. Other proteins become amyloid too.
But you're also saying it is not the infectious agent.
Correct.
You're saying, what is the infectious agent?
Correct.
What is? I'm asking you, what is the infectious agent if it is not? So this misfolded prion protein is, you're saying that's just a result of the infection, or no?
So that's why I gave you a slide to look at. I mean,
we'll get to your slides, Laura. We'll get to your slides. Be patient.
I think the point is you have infection, you have infectivity. Infectivity being the infectious agent. You're directly looking at something which is infectious.
Yes.
Which is transmissible to animal after animal after animal and produces a disease.
Is it contagious?
No, it's not contagious. People use that word. I actually saw it used in hepatitis the other day.
I'm going to check. Big check mark.
Hepatitis, serum hepatitis is not contagious.
The reason I'm laughing, Laura, for the listeners is I told you there's so many of my colleagues and experts who have actually said, instead of saying it's a transmissible blah, 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 they'll say, CWD is a highly contagious. I've seen it multiple times.
Yeah, so, they've also, some people are silly, they call AIDS contagious. It's not contagious. You need to transmit it by direct contact and where you insert something. It's like contaminated blood, a contaminated needle, okay? It's via a sexual lesion, okay? That is how you have to transmit it. It doesn't come through the air. It's not indirect. It doesn't come from the water from somewhere. Now, if you have it on a post that a sick sheep is scraping himself against, and that's dried blood, okay? And it should be, at that point, highly infectious because the animal is very sick. The infectivity goes up. It's not like a hit and run, like you can't see it anymore. It's there. And another animal goes and brushes against this and excoriates himself against it. Or you're shearing if you ever watch shearing, I mean, it's a pretty bloody procedure. Mm-hmm. You're not sterilizing the shears each time you go to the next. So you basically have an ability to spread. When something is dried, you can barely decontaminate it, okay? It's like it's become encased in serum proteins and everything else, okay? But it still can be transmitted. So blood is a really important thing. The first paper that Prusiner quoted, and people ignored it. And it's really important. If you don't mind my going back to what we discussed, I asked you, he said, what do I think about how it's transmitted? And I said, well, the deer have horns and they do fight, don't they? The males for the females. You said, oh, yeah. And I said, that's pretty bloody, isn't it? Yes. And then you actually astounded me. And I said, so I'll bet that's one way of getting it. And you said, more male elks get it than females. And that already tells you that blood is one of the most, and direct inoculation is one of the most effective routes.
This is one of those things that it has been reported, that prevalence, which I don't like this word at all personally, and it doesn't matter why. Prevalence has been reported higher in the male segment, and you and I had a at-length conversation about that. And it's bothersome to me as a biologist and a manager because there's a conflict of interest here. I'll be completely honest with you. See these big antlers back here? I like big antlers, and big antlers come from mature bucks. I do not believe in killing a buck before he reaches maturity.
Right.
So in my state and many other states, once chronic wasting disease is found, they start one of the major management recommendations is to kill more does. And one of my questions in this CWD, there were 5 slides I think I counted in sequence that said we must kill more does. We must harvest more females. And I said, I'm just curious. And this is so hard for me to say because the last thing I want to see is managers and biologists out there killing more males because the prevalence is higher. But let's face it, if we're being honest and true to science, if the males have a much broader home range, they take these crazy excursions, they fight, they do all kind of stupid male shit. If you want to control the
including beat up their mates.
Exactly. For the fun of it sometimes, right? Even after the score's been settled, they do. Why are you so heavy-handed on killing does to slow the spread, which is another one that makes me kind of ill. So, yes, you and I have had that conversation at length, and I've asked you about blood. Laura, can you tell me more about blood? How come no one ever speaks about blood?
Well, first of all, they can't find prion protein when an animal is infectious but hasn't developed disease at earliest stages. And clearly it's so. Hadlow did this beauty. May I go back to an old experiment, which I always tell
Please
people?
do. But they tell my fellow scientists tell me anything that's older than 5 years you should just throw out, which clearly I could see where they're going.
So there's a very, very famous paper by Eklund, Kennedy, and Hadlow. And what they did is they injected scrapie brain into a region near the sciatic nerve.
Laura, I got to pause. I have to pause a minute. I'm sorry. For some reason, my computer is not plugged in. I got to make sure my battery doesn't die. Hang on a second.
Yeah, I almost lost my computer too this morning. I forgot it wasn't plugged in. The file looks wonderfully great.
Sorry about that. Can you hear me?
Hey, you have an elephant in the back. Have you been in Africa?
A breaker? No, there's not an elephant. There's a black bear. There's a bison over there.
It looks like from here. It looks like it has a tusk.
Oh, okay. Sorry, but the breaker tripped.
Oh, now I know what it is. It has a white patch in its chest.
Yeah.
That I thought was a tusk. No, I now see its head.
So a breaker tripped, and my power was not on. So anyway, where we were is I had said to you, tell me about blood. Tell me about the blood.
So I have to tell you about Hadlow. So there's this wonderful paper, Hadlow, Kennedy, and Eklund. And don't forget that I come from a background where I had to lecture about all the viruses to first-year medical students, so I learned a lot. Okay, and my husband did that's how he got to the United States. He was working on tertian disease and then polio virus here. Okay, so basically, they injected brain homogenate near the sciatic nerve. The sciatic nerve is in the thigh, and it really has direct access to the spinal cord. So they thought, okay, if it goes by the nerves, it's going to go, you'll see the spinal cord first, etc. Now, in fact, what they found that the spleen, they did these experiments. They looked at spleen and lymph nodes, and they looked at brain infectivity. Now, this is a huge experiment. Basically, every week, they would take a sample from animals that they injected in the sciatic nerve, multiple animals, okay, multiple sheep. I think it was sheep, yes. Or did they do it in mice? I can't remember. But I think maybe they did it in mice. Maybe it was with the Chandler string. And they took it every week and they would take these samples, okay? So they have to kill the animal, take out the spleen, etc. And they would do assays of the spleen and assays of the brain. They'd homogenize it up and inject recipient animals to say which
Assay is
ones
just a
get
test, by the way, just a
It's-
test.
Yeah, an assay, a test, but it's a test of it's an infectious test.
Yep.
It's in a test of the infection. If the animal gets sick with all the same symptoms and et cetera, it shows it's biologically replicating itself. Okay? Fine. And what did they find? They found that it went into these organs. How did it get there? Well, the obvious, it would have to go by blood. And it went into the brain much, much later. Okay? And how did it get to the brain later? Probably by the blood. So but people had actually tried, Gadashek tried, and they took serum and they took whole blood and they did some experiments, not really exhaustive, but they did some experiments and they didn't get any infection from blood. So Manuel said, well, of course, why don't we take white blood cells? That's where polio traveled to get to the spleen. So let's isolate white blood cells. That was his brilliant idea. So we took white blood cells at all these points. And when he injected the brain, okay, it also didn't go to the brain. It came out because some of the, as he said, because obviously you inject with a little syringe, some of it's going to escape. You make a little hole in the brain. Even though it's a microscopic hole, it seeps into the blood. And you get infectivity, and then you get a hiatus. And then what you find is the disease goes on, okay, as the incubation time goes on, okay, and the animals are healthy and look fine. This was in guinea pigs that lived for 12 years. Basically, infection begins to come out about halfway through the incubation time. And the incubation time in those animals is shorter than normal. So let's say guinea pig usually dies within 180 days. These animals get sick at 500 days, 400 days, and et cetera. And then as you go to the end of the disease, when their brain is falling apart, okay, where they have a spongiform changes and everything, you have very high infectivity, and the animals get sick as if they were given maximal doses. Okay? So basically, that showed it was in blood, and it was in white blood cells. And furthermore, when you do these experiments, and we've done them, microglia is a kind of myeloid cell in the brain. It's highly infectious, and it doesn't have abnormal misfolded PRP that you can detect. But you can see the misfolded PRP in cells of the gut. You can see it in spleen cells, and you can see it in dendritic cells of the gut, which is a myeloid cell. So clearly, it is spread by these kinds of cells, and they get in and they transit and they go and they infect other cells. Now, I want to make something else really clear, because people are now talking about transmission of prion, misfolded protein. Okay?
Yes,
From
please
cell
do.
to cell, from cell to cell. It has been known for 100 years that proteins can go from cell to cell. Okay? This is not infectious transmission. Cells can make stuff and have certain kinds of junctions with one another where it can go from cell to cell. They can touch one another. This is not an infectious transmission. Is basically all sorts of things get into a cell from another cell. It doesn't just necessarily come from the outside. If you take cells that are infected, they need also to make contact to make the transmission of an infectious agent. Okay? So if you put a filter between them, they're not going to spontaneously become infected. Okay? They have to have a contact where they can basically share things. So again, the word transmission is a very tricky word to use. It's much better to use the word infectious, meaning you're transmitting an infectious agent, which then you can transmit again serially in a usual way. And the best way to do that is, so this is this whole complication
Yeah.
of language, which I wrote about in one paper, with words are being used in a very different way. A computer virus is not a virus. It may make you emotionally sick, as I wrote, but it's not it's not a real virus. It doesn't replicate itself, in somebody else. Do you understand what I'm saying?
Yes,
So
yes.
it's again, and I think that this is what you really have to realize. And people begin to take this into the amyloid story, which is much more financially important
Yeah,
for
yeah.
for funding and et cetera. And that's why prions have become so important in the Alzheimer field. And now everything is a prion, but none of those diseases with amyloid are
Are
transmissible.
transmissible, right? That not to
They're
interrupt you,
not
but
infectious. You can inject it and the amyloid junk is going to be left in the brain. But that brain will not transmit again to an animal. It
Laura,
won't transmit the infectious agent.
is CJD, Creutzfeldt-Jakob's disease, is that the only TSE in
No.
humans? Okay, I just wanted to,
So can I list them? Because we're
absolutely.
the only can I
I
list some of
I
them?
sense that you're
Because
going to anyway.
because
Please do.
we're the only people who actually works besides Tateishi
Right.
in Japan who transmitted the an Asian form of CJD, okay? Which I call FU, The students find that very funny, but basically because I can never say the word Fukuoka correctly, but that's where it's from. That's where it's from. And basically, it's that strain is not found in Western nations and et cetera. But the typical sporadic CJD, that's one, and it doesn't. Mice don't like this agent, and they basically are very resistant to it. Hamsters, they're very happy with it. They get the disease very, very fast. Okay, and we've transmitted lots of cases to hamsters. Guinea pigs, that we had also transmitted, but they were too expensive, the inbred guinea pigs we had to keep going financially. Okay, but they'll go to ordinary Syrian hamsters. Okay, so that's one sporadic CJD, Asiatic or Japanese CJD. Okay, it's a different strain, and I can show you a picture of it later. Kuru. Kuru, it's been claimed that Kuru is sporadic CJD. It has a different incubation time. It has a different look in the brain. And if a mouse, take them all and compare them in a mouse, and you can tell them by incubation time and where the lesions are. There are marked differences. That's number 3 as a strain. Okay. Number 4, you have VCJD. It's called VCJD, which is a BSC transmission to people. And again, some of those people with a certain mutation in the PRP have more susceptibility. But basically, people, slough the cow disease off. Cats are wildly susceptible to it. That's how they began to see the epidemic in full force, because the wild cats in the zoos, everything got the disease. Okay? Now, what's happened with that? What's happened with that is basically by removing the animals and by having strict things about, or the cows, they say, okay, we're not gonna keep the old cows. We're not gonna put them back into circulation and use their brains as feed and everything
Mhm.
else. So that basically epidemic has gone way, way down. It's practically, for all practical purposes, disappeared. Kuru was transmitted by ritual cannibalism, meaning they cut themselves. You didn't have to eat it. They cut themselves because it was part of the respect of the ritual for the dead.
Oh,
Okay?
really? I didn't know that part. I knew they
Oh,
had
yeah. That
they can
Gadashek even said it. Everybody gets so excited because of cannibalism and blah, blah, blah.
well, it's everything I've ever read about Kuru is that they took their deceased and they cooked and consumed their body
No, no,
parts
no. It's a
to
whole ritual. They cut up the brain fresh, and the women and children do this. That's why the children get it. So,
and
why
this
they're
is
very
in the
young cases.
southern Pacific, like Papua
Yeah,
New
New
Guinea, that
Guinea.
time.
It's in
Yes,
New Guinea.
yes.
It's in New Guinea. So it's not, it's really, so they cut themselves, I mean, Gadashek describes the ritual, and et
Yeah,
cetera. So,
yeah.
okay. And there's a nice direct transmission, right?
Mhm.
Okay. That has totally disappeared once they stopped having that ritual. That tells you that something that's around, you can actually stop it. What can you do with CWD? That's more difficult. You don't have a population, you can say, okay, just stop doing this. But in terms of BSE cases in humans, it's gone down. In terms of the animals like the cats in the zoo, it's gone down tremendously.
Well,
Meanwhile, it was shipped everywhere in the world.
okay. So I haven't obviously lists and lists of questions, and I've just figured we would just shoot from the hip, which most scientists don't like. I guess what if I were a listener right now, I try to put myself in their shoes. There's already been some vernacular and some things that are kind of medical school deep in the weeds,
Like what?
amyloids. Well, but we haven't gotten
Well,
there
okay, I
yet, but
wanted to show you a picture of an
we will.
amyloid.
We will. I guess what I would be asking myself, and this was one of the first things I asked you. Okay, Laura, assume it. Oh, you're gonna get mad at me. You're not your belief, but you know this to be a virus, right? You know this
No,
to be a slow virus.
no, no.
Go ahead, expand on
I
that.
think no. What I say is that the best fit model is a slow virus. Okay, to prove that it's a virus, I think you have to show that there's some nucleic acid that is specific for this. And that nobody is willing to really look at. Nobody looks at nucleic acid. So, I'm here with myself and maybe one other person who helps me sometimes. You know, Nobody wants to know. Nobody looks at this stuff.
Is that expensive? Why is that? Is it exhaustive? Is it
Well, it takes money. You have to do deep sequencing. You have to make a lot of stuff. It's good if you have a lot of animals. Basically, it's also being clever. So, it's very easy to find stuff once you have it, like infectivity nucleic acids. There always is some mitochondria associated in that fraction, no matter how you purify it. So you get down to these little particle fractions that are almost pure, but basically they're still going to have some mitochondrial stuff. Mitochondria contain this little genome of 16,000 bases. So you can find that. All you have to do is be a PCR of it. All you have to do is extract the nucleic acid, and you can take the little sequence. We said we went through the whole thing. We sequenced the whole thing of mitochondria that would come down, and it's true to form,
Mhm.
okay? But we also found other kinds of circular elements. And fortunately, somebody else in Europe, Sir Hausen, also found them in some of his stuff. He has a very different theory about them, but clearly somebody else has found these things. And they're related to phage, a phage of a Decinobacter, which is a very common contaminant, and everything on it's people who veterans have it, people in the wars get it, because it's all over banisters in the hospital. But it's the phage. It's a little piece of the phage that has a little replications thing. So I think there are more things there, but you need manpower and you need some sophistication. I was able to find them by using a different enzyme that nobody had used to look
Yeah.
just at circular DNAs.
And I
So,
know
but
go ahead.
let's go to your real point, which is the basic. If it hops like a bunny and it has long ears like a bunny and it has little white fur like a bunny and it makes a little cotton tail and it nibbles your garden like a bunny or your lettuce, it's probably a bunny. So let me tell you that the preponderance of evidence biologically, it behaves like a virus. It spreads like a virus. It has a ability to persist like a virus. Okay, it causes disease of a certain type like a virus. It elicits a host response to itself, an innate immune response via interferon and then via cytokines and everything else. So the host recognizes it. If you take this out of an animal and it replicates very slowly because it's being contained by the animal's immune system, it's not antibodies, but it's an innate immune system, a very, very simple, more primitive, but very important immune system. And if you take it out of an animal and put it into a tissue culture, instead of taking 10 days to double, it takes 24 hours.
Hmm.
And you can take all these strains and you can put them into a tissue culture of mouse and etc. And you can grow them there and it has a different PRP than it had before in a hamster or something. And you can take it out after years. It has a different PRP folding, okay? But it induces amyloid and it replicates. You can measure it by infectivity assays and, and then you put it back into the animal and it does the same thing and you can serially passage it. And it goes just back to what it did. And if it goes to a susceptible host like a hamster, it goes fast. If it goes to a mouse, it goes back to being slow.
Laura,
Does that help you?
if I didn't know
And
any better, I would say, so what you're,
let
I
me
would
just say
ask,
the
so what you're
last
saying
thing,
is
it
this
has
behaves like a
little
virus.
and it behaves like a virus. And it has a strain specific capacity to keep its identity. Prion protein that's misfolded does not breed true. The agent breeds true. If you put something into a mouse, it has mouse PRP as soon as you inoculate it. If you put it back into the original host, let's say a hamster, it has hamster PRP. But the agent keeps a basic identity, which is different from PRP of the species.
You know,
Okay?
interestingly, in the old data, the old research, the old papers, they refer to it as a slow virus, as a
Correct.
latent virus. And then
Right.
all of a sudden, bam, that information's gone. And someone, I know you're going to get mad at me here, but someone made the comment about, hey, and I'm paraphrasing, if you just wait until the scientists all die, your theory
Right.
will prevail. And I thought, wow, this
Well, that's
is,
what they say. Actually, somebody said when we all die, we're passe. So all of these people who now are retired,
yeah.
and most of them who died, yes, they
And
basically they shut everybody up. So
Yeah,
I will say, basically, it's kind of interesting, but that's not true because the science doesn't die.
so,
The
so
real
I've,
science, the
I've
real
read,
fact. So I want to say one last thing.
yes, go ahead.
Okay. So it behaves biologically like a
Yes.
virus. It fractionates away from the prion protein, which it should do like something that it's separate from, okay, not just biologically during infection. And 3, there are little particles that are virus-like particles that have been seen not just by me, but were seen in the 1970s, and as scrapie papers, natural scrapie and experimental scrapie, okay, and they were even seen by Dick Barringer, beautiful pictures in Prusiner's lab, and they were dismissed, and they've only been seen in infected fractions, in infectious material. Okay, they've never been seen. And in tissue culture, we showed them, and they're not seen in uninfected cultures.
So, Laura, are you telling me that when Prusiner, again, I hate to bring him up so much, but you have to,
Well, just say that the Prion Club,
the Prion Club,
because there is a club, there is a cabal,
when
there
a
is a
cabal, the
cabal. It's not
cabal,
just
that was your very first line to me, actually, the cabal. When they say, hey, the discovery of this new biological principle, right? It's not a virus, it's not a bacterium, it's blah blah blah. It's new, it's novel, it's absolutely
it's revolutionary.
revolutionary. You're
That's what
saying
he
that's,
uses.
are you telling me that that's bullshit?
Yep. It doesn't listen. It doesn't fit the facts. Period. So you can cherry pick the facts, and you can concentrate on one thing. So people say, "Oh, we can make amyloid in vitro. We can make it in vitro. We can make it into little things." Maybe there's a slightly different angstrom difference between the way the misfolding is. None of those things have ever transmitted reproducibly. None of them have ever created a strain. The only thing that I've ever seen come out that looks positive is something that looks like a contaminant with scrapie.
Which
Okay,
makes sense.
and I
Total
know where
sense.
it come. I know where it came from. I know how certain labs work.
Yeah.
I mean, certain labs don't necessarily listen. Everybody's had the experience of having someone who's casual and doesn't really keep things.
Oh, for sure.
So every lab can have something like that.
Yep.
Okay,
100%. So, man,
but
I have,
anybody who knows these strains, it's like it's just like, somebody, Einstein turned around to me, he said, "I didn't realize you were so good." I said, "I am a diagnostic neuropathologist, not just an experimental neuropathologist."
so I guess if I were a listener right now, I would be asking myself, okay, this is all great, Laura, but if we jump onto your camp and
I don't want to have a camp.
okay,
Just,
if
it's just,
hypothetically this is a slow virus, how does that change? And I know you're not in the chronic wasting disease world
right.
technically, but yeah. How would we have changed our management of it? How would we have changed our
Okay.
decision making
So
of it?
I think, first of all, I don't want to be the person who says, when I went to England in, 1987, 89, but before the whole thing came out,
Yeah.
about transmission, and I was a consultant. I said, well, they said, I said, oh, you have these farms that are infected. I said, so take the cows on the few farms that are infected and kill those animals and then make sure that you sort of put fresh animals in a totally different place.
Hmm.
Somebody's going to go take them to another pasture, another corral, another, etc. Oh, Laura, we can't do that. There are over 1,000 farms infected.
Mm,
And then they proceeded, okay, they have to, eventually they went to culling the animals. I say, you have to pay the farmers because they're going to put them in the food chain
sure,
unless you pay
sure.
them enough money, which was still done. But so I'm not going to criticize what was done, but they let it happen. We let CWD happen.
Hmm.
It was a tiny focus, and nobody was really watching about where it was spreading and seeing at the very beginning
Hmm.
because that was the focus. And once the animals began to roam around and then infect other animals or infect the environment, etc., then you begin to have the problem. So I'm not going to go back. I'm not in that part of it.
Sure.
You are.
Right.
However, I will say that if you have a nucleic acid that is specific for an agent or for a TSC, even if it's one that's common, a common sequence that they may have obviously different sequences that define strains. But if you have that, you can take you should be able to take something like blood of any animal and find out by PCR if it's there at a very, very early stage of disease and separate those animals, etc. So you don't have to kill randomly animals that you think might have it. And about the wild animals, that's difficult. I don't know how to do
Sure.
that.
Sure. Well, and that's up for
But
those in
I
the
said
wildlife space to.
one is just really a powerful technique. I mean, you can detect almost nothing with a kind of PCR test, okay?
Yeah, and we will have more podcasts specifically on, not you and I, but on
Yeah.
testing assays, etc. Okay, I won't get into. Maybe I will jump on a soapbox that this massive slaughtering of white-tailed deer indiscriminately is absolutely a knee-jerk and dangerous reaction that I cannot wrap my mind around that management approach ever. I'm going to do this, slowing the spread or controlling the spread of chronic wasting disease. That's absolutely an
I
ignorant
don't
notion.
don't know. What I do know is that I do believe that when you said that you can do the lymph nodes from the rectal area. If you look at the misfolded prion protein histologically in those, that's a very good
Mm.
test because it is a footprint that the infectious agent is there and
Yeah.
it's spread within the animal.
Yeah. The remote testing, the retroanal, and as well as the RT quick is absolutely, yeah,
But the RT
antemortem
quick
style.
Right. But the RT quick, it has to have some abnormal prion
Right.
protein
Right.
before it's going to show up. Okay.
Right.
So it's fine. It's really another confirmation of what you see by the old histological test.
Yeah. Yeah. So I guess,
And I actually believe the histological test more because I've seen the RT, all these variations of the shaking and baking and this and that, where I have friends who've done it and they said, some of the normals are positive.
yeah.
There's a background, there's this and that.
So
You see it on a histological slide. It's if you have good controls, it's can be really good.
I know you and I can get in the weeds on some of this stuff, and I had a friend who I've had many client friend who I've had many discussions about CWD, and I've shared this with him. Some of
Right.
this I don't share this with very many, but I've shared this with him that we're doing this, and he said, "Okay, I believe in your theory that we all carry around a massive number of pathogens in our bodies, right? Just think about COVID. You
Well,
had
you can
some."
say you can even call them some of them symbiotic.
Yeah, exactly. Absolutely. Until they become
Right. Right.
non-symbiotic. But
Right.
he said, okay, so if this is a latent virus, which makes a lot of sense, and it's just kind of hanging out there, they talk about the incubation is slow and we need to detect it and blah, blah, blah. What he's saying is so this is essentially an immune system. You hit the nail on the head earlier. This is an immune system issue where perhaps that individual animal who shows positive, perhaps he or she had some sort of toxin, that caused dysfunction, or
Right.
got shot or hit by a vehicle or got,
Or it
massive
had another
ticking.
Their infection.
had another infection. Exactly. So here we
Or
are
got
trying. Or got exactly. Well, when somebody says, "Hey, this is every single podcast," Laura says it's always fatal. I've got news for you. We all have a disease that's always fatal. All of us. Well, none of us are
Of course.
getting out of here alive. So
Absolutely.
the fact that most of these animals can, like, there's some research that shows, hey, they can delay onset, right? And they throw genetics in there, which this
Right.
podcast was not meant to get in genetics. But if an animal can delay onset based on
Right.
susceptibility or just delay
Right.
onset to, say, 5 years,
Right.
let's be honest. Most state agencies are not managing for mature animals. Hunters kill most of the animals before they hit 2.5 or 3.5 years of age. So if I can delay onset of cancer or you name it for 150 years, I don't need to talk about immunity. Or,
Right.
if I can delay it for till 100, I don't want to live to be 150. I'm
Right.
already seeing things I don't like at 48, right? Do you see what my point is here? And
Right.
this point has been kicked to the side. Well, that's a stupid way of looking at it by the experts. But ever since I got to know you, it makes me now think of this infection, the slow virus or this latent virus that is there. And then the animal gets injured, and then bam, the animal gets some sort of disease. It could be CWD
Correct.
and a million other things.
Right.
Sorry, I
So,
don't.
absolutely. But listen, one of the most important experiments was done by Dickinson. He did dilutions and dilutions of these agents to try to get something which was a mutant.
Okay.
Okay. And that's how he eventually made hamster and the guys like Kimberlin and say got to make the hamster fast scrapie that goes very fast and it has high infectivity. 263K scrapie, which is what Stan used to use all the time.
So these are
So,
inbred mice or
well,
hamsters.
no, it was in hamsters, but he took it wasn't Dickinson did the inbred mice for the
These no,
locusts.
no, but I was talking about
No,
Prusiner
but let me
stuff,
just finish this point. So
transgenic
he
garbage.
was doing these experiments, but as he did them, he took very, very high dilutions, like, 10 million fold, 100 million fold, and he'd inject a mouse with Chandler with a million fold less or even more. He'd go out to beyond limiting dilution. And the animals would die of old age. So he took the brains of these people, of these animals that didn't have any symptoms and injected into another bunch of mice. And some of them came down with the infection because they were harboring the infection. But just as you said, they had never gotten sick from it.
Hmm.
Okay. So one of the things is, yes, I agree with you. Is there a way to keep something basically at bay?
Hmm.
So like I had that picture of the spleen and everything, keep somebody, they have a couple of little guys hanging out there. Don't disrupt them. I mean, this is even true of tuberculosis. Tuberculosis, you're sitting around, I used to have tuberculosis, and then all of a sudden you have something else and you're going to the hospital and, like 3 months later you come in with some kind of, quote, brain tumor and it's actually a tubercle
Yeah,
from tuberculosis that's reactivated.
right. And you have, nowadays you have comorbidities and you have multimorbidities. And this is one of my frustrations for my fellow scientists. We're human beings. Clearly, we have been absolutely, I said, perfectly shitty with
Right.
managing chronic disease. There's not a single pharmaceutical out there that can fix or reverse a chronic disease. It's all acute.
So I will say that they can arrest it. And one of the great things about HIV is people were looking at the immune system because that was really where the disease was. It
Sure.
showed up in a lack of immunity.
Right.
And other things coming out of the woodwork once you lost your immunity. It's like being on immune suppressive drugs. Okay.
Hmm.
But they said, it's the virus, stupid, it's the virus. And then once they found out what the nucleic acid was of the virus, and they began to try to design something that would stop the virus from being able to replicate, they basically made a huge difference. There are people who are alive from HIV, positive infections in the 90s, and they're still alive when they take the antiretroviral nucleic acids. Okay? That's a fantastic thing. So that's another reason why, theoretically, in principle, you might be able to slow some of these diseases if you know what the nucleic acid and where its weak point is.
So
So,
my belief, not that it really matters here, but the other side likes to take this and make it crazy, but yes, I believe that nature's got this, and I've written popular magazine articles
right?
about this. I don't think that we should call it God, call it Mother Nature. Am I
So
saying that
not, neither
this,
do I. Neither
I,
do I. I mean,
I I'm not
I
saying,
think engineering cows so that they don't have a cow prion protein
yeah.
is to me,
No,
like
I think that Mother Nature will do that, or whatever you believe in spiritually will do that, will happen. A species must be fit, meaning it must reproduce to
correct.
continue its presence, its perpetual presence on Earth. And there's a biologist who I can't say I agree with on a lot of things, but when I was just a freshman in college, and Wisconsin was dealing with their CWD debacle, which
Right.
I think in hindsight, part of it was bad, part of it was not so bad, because at least they admitted at one point that, hey, we need to change this. This particular biologist got out there just because he's older than me, and I would have said the same thing. And he said, I believe in the white-tailed deer. I believe that although the evolutionary process, may be a little bit slower than what we want, right? It's going to happen. And I think if we just,
So here's I'm going to put it even in a bigger perspective.
please do.
So one of the findings that I was lucky enough to have is I found these long interspersed repeats in the human genome, and
What does
nobody
that
had
mean? What
seen
does
them.
that mean?
So there are parts of our genome which are repeats, and some of them are short. They have a repeat of a sequence. Some of them are very long. Okay. And the ones that are shorter tend to be at the centromeres, and they define part of the centromere. I don't know where they come from. Okay. But the long interspersed repeats, I said, oh, wow, in 1980 something, when I first sequenced them, I said, they have these huge, long, open reading frames. They must be coding for something.
Hmm.
They must be coding for something. There are 50 sequences in the database, the whole database. You will phone up on the modem to Caltech. It doesn't match anything. They don't know what it is. Where are they? I said, where are they in the genome? Where are they coming from? I mean, they make up at least 4 or 5% of the genome. Okay? That's a lot. They don't do anything. They're useless. They're parasitic DNAs, well, what's it? Crick. Okay, fine. What are they? So we look at them, and it's interesting because I was one of the people who helped develop with David Ward this way of labeling nucleic acids, but I wanted to use them for chromosomal localization in situ. And they're little bands in human. They're little bands along the chromosome, and they define certain kinds of sequences which are late replicating and tissue specific. So eventually, they sequenced AIDS, the AIDS virus. And guess what? Lines are derived from retroviruses. They're retroviral sequences. So not only do we resist, we can use these things. And this goes back in evolution a huge amount. So I wrote in a paper, I said, I doubt in the long history people couldn't believe I wrote this in one of my papers on endogenous retroviruses, which we looked at in different species and et cetera. I said, and different cell types. And I said, in the long history of these retroviruses, I said I wouldn't, and the intimacy of humans with sheep, I wouldn't be surprised if we gave sheep scrapie from something that was relatively innocuous for us. And if you look actually at animals like mice, some of them have xenotropic viruses, retroviruses, that will attack their neighbors
Hmm.
who they're next to,
Mm-hmm.
but they're totally immune to. They're not immune, they're resistant to.
Yeah.
Okay? And sometimes this has to do with a receptor that one or the other has.
Mm-hmm.
But it's actually a part of biological warfare too.
Yes. Yeah.
Okay? So, I mean, it's really fascinating on a much bigger scale. So, yes, I actually think that
That is a
even
big
eventually,
scale. That's a big scale. Yeah.
okay? So, I mean, so all of these things, just like the mitochondria, it's really, that's why I say I don't even like to think just about disease. You think about evolution and how we in nature, all species, all plants, et cetera, are able to sort of use certain things which may start out as infectious and then not only adapt, but actually take them in and put our own sign on it.
Yeah. Yeah. And there was a there was, well, what do I call this? A nonprofit deer organization that did an article once that called a certain group of people who question, right? CWD naysayers, or, there's a whole line of thing,
You mean that they said
you can't ask
they say
questions
there's no
anymore.
such thing as a disease?
There are people who say there's, that it doesn't exist and all that. And I'm not open to any input, anybody's data and science, etc. In this, they kind of attack those of us who say we're having this lengthy discussion that could easily be said, hey, just hands-off approach. Just stop interfering. You could make things worse. This is
Right.
nature, and nature's complex. It's too complex to just try to find one thing and narrow it down to that one thing, and actually control. I hate that word, but control, just like you hate believe, and control things. And of course, then they call us the group of, these are the, hands off, let it be, it doesn't exist. I never
Well,
said it
listen,
doesn't exist.
if you were like that in medicine, it would not be good, because I mean you would have all sorts of things that basically interfere with nature to make people better by
I
understanding
would
a
agree with
disease.
that. I think that's a bit out of context in comparing human medicine to wild populations and how we
Well,
manage
I
wild
don't think it's that.
populations.
I think there's a big difference between a certain kind of genetic engineering, which is sort of grandiose, versus something that can cure a disease. Okay, so I think there's genetic engineering that can cure somebody of a mutation. I mean, I am very happy to see what's happened in sickle cell anemia.
Yeah, I
I
would
hope that
agree with human
okay.
beings, but it also this also there's a
But even for an animal, I mean, you could say, well, this animal has other features, or this plant has other features that are really great that we don't have in other plants. So we don't want to lose these wild species,
totally
but
agree.
we want them to be able to breed. But they're not going to breed if they die from something that they can resist. If we put something in that will stop that infection from going.
Right, but there are also areas like Wyoming and Colorado and even parts of Illinois and Wisconsin now where you see, the prevalence spiked, right? Because we're looking for it and obviously we're finding it. Prevalence is increasing, and then bam, I guess I'm on camera, I got to go this way. It hits a plateau.
Right,
And although
right,
it may do a little blip, what people don't realize is kind of looking at the value of gold over time. Well, I'm sorry, it goes like this, and the value of the dollar goes like this. These little blips in time, it's hitting a plateau on its
right,
own, and perhaps will start to go on the decline. And they fear that kind of stuff. They hate talking about that kind of stuff. But
right.
again, I'm not saying that it doesn't exist. I'm not saying that you should not do any kind of testing or any kind of research. I just think that my peers have missed completely. You used a word in relation to TSE research one day that I think fits like a glove. You said the way that this has been handled has been sloppy. And I may be taking that out of
Right.
context, but that
Right.
word, I
The
think,
language, right.
it's
It's
been
been sold
sloppy.
and oversold.
Everything has been sloppy. And I think at some point we have to be okay admitting that and asking better questions. And that's when I ran into the Manuelidis first reference to your white blood cells. And I said, who are these people? And then I
And
found out that it was you and your husband, and did some research, and holy crap.
yeah, and other people who were good in the lab too. They were good. We had some great veterinarians. We had some great other people, who were here, and they stuck with it. They stuck with it. But it's discouraging for people who are interested in this field, because I had somebody, and basically they said, "Hey, you go with Laura. That's the end of your career in science." So
I don't think that's silly. I believe that's why I invited Stan on here, and I invite anybody who wants to talk about CWD.
But again, I don't. I just think that that's a sort of conflict of interest for them to even talk that way. I
Yeah.
say if you want, I have said people, you can ask people in my lab. I said, if you can do an experiment to prove that the protein is infectious,
Hmm.
that is fine with me. I
Hmm.
said, but I'll warn you that I'm not going to necessarily say you can do anything you want when I already know that that technique won't work because I've tried it.
Yeah. Yeah.
I
Well,
said, you can try it up to a point. I mean, I'm not going to let you go off the deep end and not getting anywhere as my student.
yeah.
I want you to be able to have something that is a substantial piece of scientific work, no matter what anybody thinks.
I'm going to kill this fly. I've said this in the past that, I believe that most 5-year-old children are better than most scientists these days, because if you ever hang around a 5 or 6 or 7-year-old, well, why is this blue? Well, it's blue
Yeah,
because that's what your eye sees. Well, why does my eye see that? Well,
right,
it's because of these cones and rods and blah, blah, blah. Well, and the light bouncing off, they keep asking questions. And many of the scientists I'm around, when I ask a question, they just want to say, it's Prusiner. Haven't you read Prusiner's work? And I laugh because I've read Prusiner's work dozens of times. And in fact, if you go back to when you had mentioned you'd been doing this longer than Stan Prusiner,
right.
and you look, there's a lot. There's a lot of disagreement. There's a lot of back and forth,
Absolutely. It used
but
to
we
be.
don't hear about that anymore.
Right. No,
Ever
you're not
since he
allowed to
won this
disagree.
this Nobel Prize, it's like it's put to bed. This is it. Let's not
Well,
consider anything
listen,
else.
this is the problem with Alzheimer's amyloid. It has been a dead end, and people got really ticked off at me. What was it, 30 years ago, 25 years ago, when I was on the committee to advise Congress? It was a great thing. There were lawyers, there were patient family members, to discuss this was going to be the great new aging institute. And boy, there was like, it's only beta amyloid. All we have to do is have an animal model of beta amyloid. And this is what it is. And there are people who say that. And we have drugs out now, which are dangerous, which cost thousands of dollars. And we're giving them to people. And I've seen some of the people blowing out their brains,
Mhm.
Vascular stuff and et cetera, as a thing of this.
While somebody's getting really wealthy.
Even if they take it, how much does it help? Oh, well, like they have 4 or 5 weeks more of being a little bit happier or whatever. You know, I mean, and to me, that is, I see these people, I review some papers. I mean, people will just like, oh, we can then do this and then do that and give it to people. I said, on what basis? On one experiment in a mouse,
Yeah.
which has a different system and it's not even reproducible and it doesn't even do that much.
Right.
There are some that are good, but they involve all sorts of shenanigans and genetic manipulations, which you're not going to be able to do.
And for many, many years, when I read the science back in the 60s, 70s, especially 80s, and then 90s, even after 97, when he won the Prusiner won the Nobel Prize,
Right.
people kept saying, hey, this is not reproducible. The only people who are producing these data are those either Prusiner in his lab or those who are associated with Prusiner. Now, I haven't been here. Like I said, I was born in 78. So a lot of this went on as I was a child and didn't give a damn. But have all those experiments actually been reproduced by a peer? And talk about peer review, that's a whole other topic, but have any of these things, or have they just become fact because
So the
everyone...
most important one, the one that has finalized the belief in infectious prion protein, some form of infectious prion protein, is the claim that recombinant PRP, when it's misfolded, becomes infectious. And Collins, who's a big believer in the prion theory in the UK and has masses of money, so he can do all the infectivity assays, which are expensive, okay, and time consuming, okay. He's done 20,000 experiments, and not a single one of them, using either the Marr model or Prusiner's model, has been able to show infectivity that is reproducible. They get a little something in the first passage or the second passage of the cells when they assay, and it peters out. 20,000 negative experiments.
Wow.
Now, in one of the abstracts, he writes, well, we just don't have the right folding. We haven't found the right folding. I said, maybe it's something else,
Yeah.
Maybe maybe there's another molecule or molecules involved. Okay.
Interesting.
But it is closed. It's a closed book.
You mentioned something I started doing some reading about, in the Journal of Alzheimer's Disease. They talk about, obviously, these are...
They're all prions.
Yeah, sort of, I guess. They're
They're
all
seeding.
prion disease, yes. And I found it interesting that they're struggling with Alzheimer's disease and ALS.
Right.
And at the same time, we're struggling in the wildlife arena with chronic wasting disease. And it's because everybody's reading from the same playbook. What if we
Right.
start to ask better questions? And I'm not saying Laura Manuelidis is correct, but why are we still calling the same plays when the defense is shutting us down? At what point do we become real scientists and say, let's ask different questions, let's ask better questions, and let's look at the alternatives?
Let's try the experiment in a different way that doesn't put the limitations. Oh, you have to find prion protein.
Yeah,
Otherwise, you just throw it away. No, no. What's in that stuff that doesn't have prion protein? Is it infectious? I mean, these are the things that you have to take it to the next step.
sure.
Why should I only incubate in proteinase K for 15 minutes or 30 minutes? Why not just keep incubating it?
Hmm.
And then we did that. And the prion protein disappears. We can't detect it anymore, but it
Interesting.
maintains high infectivity. Oh, well, it can be one molecule. That's the argument of Charles Weissman.
I read somewhere, and I don't know if this is true, so fact check me on it, that Stan Prusiner had obtained over $40 million in funding, just to put that into perspective for people. And I don't know if this was to date in that article or in his entire career. It doesn't matter. Just take $40 million. And a lot of these, the research you're talking about in these, what you would love to do costs a massive amount of money. And you have to go get that money.
Well, he put a lot of the money into making these transgenic animals, and so did Weissman. But what have they really shown? They've shown that if you change prion protein, it may have no effect, or it might have some effect, you know, but it's not strain specific.
Yeah.
It just came out with nothing. If you have a lot of it, the animal will get sick spontaneously.
Yeah.
Why? It dies at a relatively young age, and it has all sorts of holes in the brain because you can get holes in the brain from all sorts of things. And if you make a lot of one membrane protein, 60-fold amounts, you're going to gunk up your system. It's not going to work.
So as a neurologist, would you like to talk about where these holes come from and why these holes are there? Or
Sure. I mean, I have a picture. I have a picture.
do you want to
of
jump into some slides? Do you think?
Yeah, I'll show you a
I,
couple of slides.
I know
Let me see what you have. I'll tell you what slide to go to about
remember
holes.
I'm
So
a rookie with this.
Let's go to slide 3.
Hold on a second. I am a rookie at this. So understand when I do this, I'll probably disappear because
So the infectivity basically collects in synaptosome mitochondrial fractions. Synaptosomes are places that nerves connect with one another. They're the ends where they communicate, and they have little vesicles. Go to number 3.
can you see these, Laura?
Yep,
Am I
it's in
doing
the
good?
left. Yep, perfect. But you go to number 3, light up number 3 slide. Go down from the beginning. That's 1, 2, 3. Keep going. 2. There it is. Okay. So I don't know if you can make it bigger, but basically, that's a dendrite.
It's not big enough?
Well, you can try to on the slide and make it a little bit bigger if you can.
Hold on a minute. Keep talking.
No, you have to go back.
Yeah, keep talking. I'm a
Oh
biologist.
no, I mean you can see enough even
Okay.
at low power. So you see there are big D's over there. You see that?
Here,
It says a red D. There are 2 D's at either end of
I
that.
do know how to do this. Can you see my laser pointer?
So there's a D there and there's a D higher.
Up here.
And and that is a dendrite that is receiving synapses, which are at the little arrows.
Right here.
It's a process, right? The little arrows, and actually they have vesicles and etc. So that is where the disease really begins. The disease, okay, where the neurons are falling apart,
Mhm.
okay? Now, what happens is neurons and dendrites basically are, are dying, not the mitochondria, but they're dying and they're falling out. And so they begin to lose their contents and they begin to disintegrate and leave a hole. And you can see them as little holes if it's in the middle of a neuron that's big. And you can see them as little holes in cross section of a dendrite, which are going to be across, like if we cut across one of those ballooned areas of the dendrite. Okay.
So I've heard many of the experts, I guess I'll say, mention that these holes are created because you get this cluster of misfolded prions. And
No.
someone will say, well, how do you get a hole when you get a cluster of misfolded prions?
So if we go to, first of all, okay, so let's switch to what amyloid looks like when it's isolated from synapses,
Okay.
which is where, by the way, those are the places I can tell you where Barringer showed all of the particles, the infectious particles.
Mhm.
In those regions, okay, not prion protein, he showed these masses of little 20 nanometer, roughly 20 to 22 nanometer particles that were dense,
Mhm.
that looked like viruses, okay?
Okay.
And that was in hamster scraping the synapses.
And you want me to go back to amyloid?
So now I'm going to show you what amyloid looks like if you make it from a synaptosome region which has, so the prion protein is in all the membranes of those cells.
Okay.
Okay? And if it misfolded, it can be misfolded, but you don't necessarily see it inside the cell. I'm going to show you, you can see it inside the cell. I'm going to show you tissue cultures where it's inside a cell. And I'm going to show you first what happens when you isolate synaptosomes that are infected. And then all you have is this little fluffy stuff. And if you add a little proteinase K to make the prion protein misfold and become amyloid, what you get is slide number 6. Go to 6.
Did I get it?
Okay? So those form, and I mean, we showed pictures. This happens to be from a synaptosome preparation that was done in our lab of CJD, in collaboration with Pat Mertz, who did the electron microscopy, and Robert Somerville, who did the fractionation. And we looked at it under the microscope, and they were called scrapie-associated fibrils because Pat first found them in scrapie animals. Okay?
Mhm.
And we said, are they in CJD? And there they are. Now, you know that there's this big theory about you seed something in the amyloid when it's broken up into little pieces, it's seeding something. Well, if you take these amyloid preparations that are still infectious, okay, because they're from synaptosomes, and you break them up into little tiny bits by sonicating them to death, the infectivity does not become increased.
Hmm.
So the seeds don't change anything when they're small or big. Now we're going to go to slide. I'm going to tell you which slide. We're going to sit down to slide 27.
Oh boy.
Yeah, I know.
27?
Yeah, 27. I'm going to show. I'm
I
not going to.
cannot see. So we're past the blank?
Yeah, pass the blank.
Oh
It's the
boy.
last slide
All right, you'll have to tell me because I can't see
because I
slide
promised
numbers.
I said I would show you there. You just skipped it. The last
I'm
one.
here.
There it is. So you see this?
Yeah,
This
real
is
quick, Laura, before you start talking, amyloid, can you explain it to a 5-year-old or a 5th grader? What is amyloid?
Amyloid is a protein that's taken a beta pleated sheet, as described by George Glenna. It's a beta pleated sheet conformation and packs it in as an array.
Which means it's infectious or no?
No amyloid except prion protein amyloid has ever been shown to be infectious.
Okay.
Right? Okay. Right? There are lots of
Just
amyloids.
checking. I'm enjoying
Okay,
this.
fine. Okay, so you see those fibrils under A. You see they look like they're these straight fibrils, just like the ones that we isolated. But here it is, and it's actually in a clump in a highly infected cell.
Mhm.
And those little black dots above it, okay, that's actually that's antibody labeled with silver grains, okay, to show that amyloid is made from prion protein.
Hmm.
It's binding to prion protein, okay?
Okay.
And it's associated with membranes, and you see this in some highly infected cells, okay?
Okay.
But you can also isolate it, and if you isolate the amyloid, it's not highly infectious. You usually lose about 95% of the infectivity if you isolate the amyloid itself. Now we're going to go back to, I'm sorry about this, we're going to go back to something. I'm going to show you the difference. I'm going to go back to one other thing. Can we go back to the separation of infectivity from prion protein, or do you want to go to the particles?
That's totally up to you. You're the boss. I'm just a
Okay.
terrible slide sorter.
Okay, let's just go to something that's been known for a long time from our lab. So now let's go to slide 9.
Tell me when I'm there because I do not have.
9.
I don't have the numbers.
That's it. That's it. Okay. So in this slide, At the top, we ran a gradient in sucrose. So if you put something in, things at a viral-like size will go down and ordinary proteins will stay up because they're not as dense or as big in terms of a particle size
Mhm.
as a virus, okay,
Mhm.
that has nucleic
So just to
acid.
be clear, you're trying to figure out the size of this thing.
Correct.
Yes.
Correct. This thing. Okay. That's right. Absolutely.
This kind of goes back to the if it behaves like a virus, it's a virus. So let's see.
So the slide at the top shows we don't know where the infectivity is, but we took every fraction, all of those fractions, you see, they're represented by little bars
Hmm.
of the gradient, and infectivity was down at the bottom of the gradient, and it had a certain S value called sedimentation value. And when you look at that stuff by other means as well, like chromatography and field flow fractionation, it corresponds to something that's a viral size,
Mm.
about 20 to 30, 20 nanometers, 25 nanometers. And in that fraction, you find those little particles. You see the NSAID at the top.
Hmm.
There are these little particles that are with a small arrow and a big arrow. They're small. Yeah, that guy. And they're 20 to 25 nanometers. Okay? All right. You also have a couple of other little fibrils, but they're rare and they're amyloid fibrils. They have a little helical kind of twist. Now, if you look down at the bottom, you see an assay for prion protein. Okay? And you see that most of the prion protein, in fact, about 90% of it, is at the top of the gradient where there's no infectivity.
Up in here.
Corresponds. It, no, the top of the gradient is light, so it's where there's no infectivity. Go to the top. The top is at the right. Yes, and you see that has no infectivity. It corresponds to that little arrow over there with infectivity above it.
Hmm.
It corresponds to the gradient. And then you have a fraction that's at the basically in fraction 2, which has some of the prion protein left over. Okay?
Hmm.
Now I want to go to the next slide directly after this. And this is what the particles look like when they're in a cell. Okay? And they're the same size. They're 20 to 25 nanometers, just what we expect from the gradient.
How
And
big is
that's
a virus
only
generally?
so the viruses range from about 50 viruses that are, from circoviruses on range from about 15 nanometers, and then they go way up to almost rickettsial size.
Hmm. Okay.
Pox virus, huge.
Got it.
Okay. Another couple of orders of magnitude.
Hmm.
So poliovirus is about 35 nanometers. Okay. So this is smaller, but it's not the smallest. Okay.
Okay.
So this is only in infected cells, and you see the same particles of this size in the gradient where it's infectious. Okay.
Good deal.
So theoretically, one possibility is it, and when you isolate or you purify these particles as much as possible, it's when you have a lot of infectivity,
Hmm.
not necessarily the prion protein. So this is what takes a lot of work because there's, doing gradients and doing assays and isolating something more to be able to say, I'm going to find the nucleic acid that is specific for the particle rather than any other junk that might be around
Hmm.
takes time and
Sure.
takes effort
Sure.
and you have to do infectivity assays. And even though we have them going in tissue culture, which just is incredibly different because it makes us able to do a number of things. Most people don't have a tissue culture system where we can look at different strains of agent in the same exact type of cell.
Hmm.
Okay. We have the ability to do it, but obviously they're not going to give us any money to do this. So that's fine. Now, I'm going to show one last thing because I mentioned strains. So if you go back to the picture 7, actually, first we're going to go back to picture 4. I take it back.
4.
Number 4.
Which one was 4? I don't have.
It's after the EM. It's after the. That's it. Oops.
Oops.
Number 4. That one more down. That's it.
Hmm.
So here we have, just like Hadlow, the infectivity assay after you inject the brain. Okay. and you assay for how infectious the material is. And basically, we injected about 10 to the fifth, and it disappears the first couple of days. So the red line is we're measuring infectivity. And this is a log scale. That's right. And all those points are assayed points.
Mm-hmm.
Okay? And it goes from 10 to the third all the way up to 10 to the seventh. That means it's 100,000-fold or more increased.
Mm-hmm.
That agent has replicated. It has been reproduced in the cell, or been able to reproduce itself by doubling and doubling and doubling in a very consistent way along a straight line. Okay? And only at the end does it become a plateau where it stops replicating.
Sure.
Now, you notice what's happening at that point is you have an arithmetic conversion of 50% of the PRP, okay, into a misfolded form. And that's the scale on the right side. And that starts just when it's very, very steep and it doesn't match the curve of infectivity,
Mm-hmm. Mm-hmm.
okay, and it's late. And when that starts, the plateau begins to stop.
Mm-hmm.
Okay?
Which
So the
so
prion
right in here
protein,
would be
that's right.
an important,
That's right. And we've done this with rats. You have a slide in. I'm not going to show you. You'll just have to
So
believe
stupid
me.
question. What happens if you continue on for another 100 days, 120 days?
Oh, the animal dies.
Got it.
Clinical disease is where the arrows are.
Okay. Fair enough.
Okay, so the prion protein comes on just a little bit before, misfolded prion protein comes on just a little bit before the clinical disease.
So to the average onlooker, then, what is this proving to? You're at
So
a
the
family
first thing it
function.
proved
What does this mean, Laura?
So the first thing it proves is that the infectivity has nothing to do with the conversion of PRP res in any direct or linked way. Those graphs will never intersect. And it also means that the prion protein may be part of an innate immune response, which traps the agent, and the animal, basically fails to be able to make more stuff or make more virus.
Interesting.
Okay, maybe because it's taking some of it out of circulation. It can't be reached anymore. It's making amyloid, by whatever mechanism. Okay? So, obviously, the next slide is the same thing. I can show you the next slide. And basically, this has a much longer incubation. And you ask about the holes. Just go down one more slide. It's number 5.
Am I going the wrong way?
No, go before. You skipped. Come up. 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 There it is. So here you have a rat, rats are great. They can take in almost anything and live with it. They live in New York City. Okay?
I would agree.
So over here, what's really interesting,
They can
you
have 'em.
asked about the holes. So what's really interesting is on the very start of the curve, very early relatively, at about 50 to 100 days, the little star shows an increase in vacuoles. Okay, and
This
it
guy here?
occurs. Yeah, the star there. Okay, and then the star, and the microglia also go up in number, which is the red. Now, just like the other, but really 150 days later, PRP res it at the very end of the curve. It's basically, that's it. You got it. Your pointer's on the PRP res curve. And there are other things, other proteins that come in a little bit earlier. One of the ones that's associated with the other thing that you see is a response is astrocytic messenger RNA also comes in relatively late, but before prion protein. So there's also a response of the brain to the agent and the infection before you have prion protein on several levels. And we did more experiments showing even as soon as you inoculate, in the first 30 days of infection, you have responses that you don't see in an animal that's actually inoculated with non-infectious prion protein.
And just in case someone's asking right now, what is PRP res?
Okay, PRP res is the amyloid form of prion protein that you see on a gel. Okay, I can show you. Okay, we'll go to one other slide. Let's go Let's go to a slide.
Is it infectious or no?
No.
Okay, what slide?
Okay. So I can show an example of a strain difference. You want to go to slides 7 and 8?
Get what I'm on now.
Okay, you're slide 6. You go to the next one. Yeah. Okay. On the left side, what we're staining for here is prion protein amyloid, because it takes up a particular antibody stain only in the way that a clumped amyloid type
And
of.
this is Creutzfeldt-Jakob's disease. This is a human
sporadic.
TSC.
This is no.
No.
This is a mouse,
Okay. This
because
isn't a
mice
mouse.
don't like sporadic
Yep.
Creutzfeldt-Jakob
I
disease,
remember
and
that.
that's on the left-hand side. Okay? And you see that has a very long incubation to make anything. It has just a little red lesion on
This?
a little, yeah, that's it, which
This?
is prion protein, right, and glial and etc. Okay. And on the other side, at 150 days, even at low amounts of inoculation of homogenate, you see the Asiatic strain. It kills the animal in less than 150 days, and you see the prion protein is all over the brain.
Hmm.
So these are totally different strains, okay?
Okay.
And you see the vacuoles down below in the one, that's right, in the one that is from the Asiatic strain, but you don't see vacuoles
And those
in the other.
vacuoles, again, are the holes.
The holes,
Yeah,
that's
that
right,
everybody
that's right. They're the
references.
holes, from a dying neuron and balloon dendrites and things
But
like
it is
that in
not
the
a
gray matter.
conglomerate of
No, the
misfolded
prion
prion
protein is little
proteins.
tiny stuff.
Yes, yes.
So then you go to the next slide.
So much
So you remember
misinformation out
you
there.
have a little picture of this. So now we're going to take a person
Mm.
with VCJD, otherwise known as beat mad cow disease,
Mm-hmm.
okay? And we inject that human brain into a mouse, and
Okay.
we get it to propagate. We transmit it serially. And you see, just look at the top slide. You see that the red is all concentrated down in the bottom.
Mm-hmm.
That's where the hypothalamus is and thalamus is. And it looks a lot different than those other two strains, doesn't it?
Mm-hmm.
That I just showed you.
Yes.
Now you take a cow, and the cow has BSE, and you inject it into a mouse
Mhm.
with the same wild type PRP, okay? And what does it do? These all are wild type mice, no Mickey Mouse transgenic anything,
Okay. Okay.
just normal mice. And what does it show? Look at the first thing. It shows the same distribution, the same lesion profile down in the bottom of the brain, just like the human transmission.
Mhm.
So even though it's been in a cow for 5 years,
Hmm.
or a human for 5 years or 8 years, they're both giving the exact same disease that is strain specific.
Mhm.
It's not prion protein specific, and it's not it's not specific for the human species or for the cow species.
A lot of people might disagree with you on that,
On what?
what you just said, even though it's
How
all
can they
right here.
disagree?
Because they do. Because they do. They like to.
No, but I mean, what is it? Here's the data.
Oh, I'm not questioning it. I'm not disagreeing with it. I'm just saying a lot of people say a
Here's-
lot of crazy shit and they don't know the truth. Kind of like going back to these vacuoles.
And going back to the difference and going back to the strains.
I've enjoyed so many times the experts in my field being asked the question of, well, what are these holes? What are these vacuoles? And they don't know what they are. So
Yeah, well, also, listen, you can get holes in the brain. This is why it's difficult. It was difficult for some neuropathologists, and it was difficult for everybody, including us.
Mhm.
I can see the difference between Scrapie and CJD, even from the vacuoles, because Scrapie has much bigger vacuoles and et cetera. So I can tell some of the stuff just from the way, and not just the lesion profile and the timing. So basically, but if one is kept on a respirator, one can get vacuoles and metabolic changes, which lead to, big holes in the brain. So sometimes it's hard to
and that's
tell,
not from a
especially.
misfolded prion protein.
No, it's not. Has nothing to do with prion protein.
Okay.
So there
sorry.
are a lot of things that can make you lose neurons and have
Sure.
holes in the brain,
Absolutely.
etc. Okay,
Okay.
so that's my
Do you want me
comment.
to stop sharing now? Are we good, or do you have
No,
more?
we want one more picture.
Okay.
Okay, and I'm going to show you what a prion protein PRP res is. in addition to something else. Number 11.
What am I on now?
You're on number 6 or 8. So down 3 or 4 slides. No, come up a little bit. Up.
This
Up.
this one right here, Laura, represents my brain.
Listen, you're tabula rasa. That means that you can learn.
Okay,
The rest of us are filled with all sorts of junk.
I gotcha. I'll take your word for it. Am I right or am I wrong?
That one just shows that the gut and everything else gets infected and gets prion protein first footprints.
Isn't that amazing that the gut is quite important in this conversation?
That's right.
How come we don't talk about the gut and gut dysfunction?
And it gets it from the blood because these were animals injected in the brain.
And real quick, for those who are patient enough to follow along right now, if you hear that the gut is crucial, when you have gut dysbiosis and gut dysfunction, you can get that from, how many herbicides are sprayed in agriculture and blah, 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 all the other stuff we talk about. Soil health.
Let me just say something. The top, go back for a second.
Yes.
The top row shows 4 days after inoculation of the brain, and you don't see anything in the brain, the gut, the spleen, or the brain.
Okay.
Okay?
Yes, ma'am.
At 32 days, guess what? You see it in the spleen,
Mm-hmm.
but you don't see any abnormal prion amyloid in the other 2.
Mm-hmm.
Then you get to 120 days. And 120 days, you have it in all 3, but now you finally have the brain getting sick and having a lot of prion protein.
Yeah.
So you see that's the hangout in the lymphatics, in the gut, and everywhere else.
Yes.
And some of those little cells are called dendritic cells in the gut.
So let me ask you, maybe a stupid question. I've never asked you this. Obviously, it hits the gut.
If I don't know the answer, I'm not going to answer.
That's fine. You can say I don't know. I wish people would say I don't know more.
It's a joke.
So it hits the spleen early. Does it? And it hits the gut relatively early.
It can. It hits the lymph nodes and spleen is usually the way it goes.
How about the rectoanal mucosa associated test or remote?
It's part of the gut system.
Okay.
So yeah, absolutely. But I don't know if it comes by the blood or whether it comes directly from the gut. So prion protein is destroyed in the stomach and small intestine, but the infectious agent is not.
Got it.
So that's the other part of the question that I don't know. Okay, so now we're going to go back 1 slide, since that's what we're going to end on. Okay, and that 1 slide shows you one thing. It shows you brain, okay, in a particle in TSE particles, okay, where you have prion protein. And the resistant part is the part in the second lane that has a plus. Okay, so take the first 2 lanes. Yeah, that's a plus, and that's right. And that's the original is next to it. And so we have all these fractions, okay, the starting stuff, and then we treat these fractions with, this is a particle-rich fraction, and we treat these fractions with nucleases, okay? Some are from CJD and some are from Scrapie. So we have 2 sets. Okay? Now, if you look at that, the ones that are starred are the ones, the untreated controls that don't have nuclease. And you don't see any difference. But now let's look at infectivity with the nuclease. So go over to the right graph. Okay? And the right graph shows you CJD and Scrapie. And when they've been treated with nuclease, it starts out and they have 10 to the 9th infectious particles per gram, okay, or per 10 to the 9th cells. They've lost 3 logs of infectivity. This is a log scale. So that's 10,000, it's 1,000-fold. They have only 0.1% of their initial infectivity left after they're treated with nucleases. Okay, so what does that mean? It means that nucleic acids are needed for infection. Nucleic acids are required for infection. So the infectious agent has to have nucleic acids.
But Prusiner, I guess I'll jump in here. Prusiner said that there are no.
On what basis? The last time he looked at nucleic acids was in 1985 or something. I refer to those papers. I mean, first of all, technically, I mean, I know something about nucleic acids. That's where I sort of began a lot of stuff, and including the first sequences. They run something on a gel. They stain it with silver. They cut off the top of the gel. And they say it's it's not, it can't be a nucleic acid. It's Mickey Mouse. They don't label anything.
Mhm.
They don't show it's nucleic acid by any standard technique, etc.
Okay,
And
so
we had
just
already showed even in guinea pigs that we could detect mitochondrial DNA by doing Nick translation. This is in the
as you could
early
imagine, when
1980s.
he came out and he said, "Hey, this is devoid. This is protein only. It's devoid of
That
nucleic
is
acid."
that is a statement which is based on no experiments that he's ever been able to show
He
that it contains
claims
none.
that he tried to find nucleic acids
He
using
did.
6 different approaches.
Yeah, what are they? Some gel with he did it with
Oh, I
Deb
don't know.
Reasoner, and Dieringer and I went to Dev and we said to Dev, "Listen, we will bet you that whatever you're looking at doesn't have, it's either not infectious, okay, and therefore it has no nucleic acid. And Dieringer is going to assay it for you because he was working on hamsters at the time. Prusiner working at 263K in hamsters, and I said, and I'll show you that if it's infectious, I will bet you that it has. If you give me a fraction that is infectious, that's verified, I will show you nucleic acids in it." And Deb Reasoner said to us at our little dinner together or drinks, he said, "I couldn't do that because, that's, I work for Prusiner and this is not, we can't do this." I said, we would even swear to you never to say anything about this if we found something that didn't agree with
Hmm.
what Prusiner was saying. But I will bet you these fractions had nothing. He never did the controls 1-to-1. Okay? This is the exact same fraction that's being used, 1-to-1.
He took it a step further and he said this is not a slow virus or an unconventional virus.
Listen, I mean, he can say, listen, he can declare that, God is a prion. It's
Can I
fine.
stop sharing so you can see me laughing
Yes.
now, or are we still, you good?
Absolutely.
All
We're
right.
fine. We're finished.
I'm just, how do you, or how do I, I'm not a techie here, but I'm going to try my best. How does something reproduce itself if there's no genetic component, I guess, is ultimately what I'm
Well, they
trying
have a
to.
cartoon. They have a cartoon. And the
Oh,
cartoon says that little seed, and this is what that whole quaking whatever it is, quaking, shaking thing is.
RT
Okay?
quick.
So, yeah. So here's the difference. It's really simple. They take this and they say, we're adding a seed. We're adding a seed, misfolded prion protein. And you see, we're putting it into a fresh sample with new fresh prion protein. And guess what? It makes a lot of fresh prion protein that's misfolded. It converts it. However, once it's converted it, they have to add more fresh prion protein to convert it again. Okay? Now, you take a virus and you put it into cell, and it makes 1 million copies of itself. Okay? You take the 1 million copies of that virus, and it's not going to make something that's from the host. It makes something of itself. And all it needs to have a cell that can equip it with the right kinds of things to make nucleic acids.
Okay.
Okay? And it makes, again, 1 millionfold. Now, the stuff with the replication, how they measure the replication, it's not the same thing as replication. Again, it's arithmetic. It's not logarithmic. And it doesn't have a timeline. A virus takes a certain time to replicate. So a bacteria can replicate every 10 minutes. So if it doubles every 10 minutes, that means if you let it replicate on good agar that it can grow on, okay, it's going to make 1 millionfold in 20 minutes.
Hmm.
Now, viruses don't make that fast, but
All right.
acute viruses make them pretty fast, okay? But they make it by using the nutrients of the cell and the building blocks of the cell, okay? Now, you need prion protein to infect a cell. That's what Charles Weissman showed with the null mice. It needs that host protein to be able to replicate. Okay?
Mhm.
Fine. And then that protein changes probably when it interacts with the agent. So I call it agent to try to be impartial in my papers. But as when I write about other people, they call it a virus, and I don't have to apologize for that. I think that they're right.
You know, it's funny
But
when
what they called small was undefined. What I call small is defined. I'm saying it has a homogeneous size
Mhm.
that's the size of a particle that's about 20 to 25 nanometers, give or take a little bit.
you're saying where there's smoke, there's fire, it's a virus. I got it.
Not
It's
only that,
it's
but I gave it dimensions. I gave it a dimension. And other people have seen these things before. And not only that, that dimension corresponds to, which doesn't mean that the one is the other, but it does correspond to infection and to titer. Okay?
I'm grabbing something here to read only because I know you want to go soon, and I know we have to go soon, and we can do more of this.
I
But
think I think you have enough. I think it went pretty well. What do you think?
oh, I think it went great. Absolutely. You have a two
Okay,
o'clock. You
great.
have a 2 o'clock.
I'm unstated. I didn't want to say great. I don't know how you
No,
thought
I,
it
I
was.
think it's great. I think there's so much to this conversation.
But we're overshot, so you may want to sort of go over with me which editing you want to do.
Yeah.
Whatever you think when you look at it again.
If you think about it, you tell me what you think we missed or what needs
I listen,
added to.
we hit a lot of big points.
Yeah.
You know, if there are things that are redundant,
I
take
think
them out.
I think at the end of the day, what it makes me like, okay, like I have some people who I know who are very, what would you call it? They're very, okay, let's boil this down and get to the, how is this going to change where we're at today? If we said, you know what, I can't believe Prusiner was such an idiot and wrong so long, screw him. This is a slow virus. Where does that get us?
Well, again, it's the specific questions. That's why I'm an experimentalist.
Yeah.
What is a nucleic acid? If there's a protein other than prion protein, maybe that protein is really important also to attack. Maybe that's the thing that protects it. Maybe if we can get to that, we can know much more about how to take care of it.
Yeah.
Yeah. So, what are the real molecules of the infectious agent?
Hmm.
Clearly, I don't think prion protein fits.
Yeah.
It's missing something. And we need to find out specifically what it's missing.
But the prion protein quite possibly or likely plays a role in this. We
Of
just don't
course,
think it's the infectious agent.
it's an essential susceptibility gene or factor. So look, when I tell you about retroviruses that basically only infect the foreigners over there living next to you who you don't want to see,
Hmm.
and it doesn't infect you, that's because you lack something called the F1Y receptor. And that's all. There are people who are resistant to HIV. They have a particular CD missing thing. They may not be entirely resistant. I don't know what the data are, but
Sure.
clearly there are people who are much more resistant to
Sure.
HIV
Sure.
on the basis of a particular CD protein.
Yeah. I think something
Okay?
that's fascinating is early on I asked a researcher at the UW-Madison, where does
Right.
this rank? Where does CWD rank on the virulence schedule? You talk about it,
Low.
Ebola, and you talk about blah, blah, blah. You know what he said to me? You just hollered out low. He yelled at me. He said, Jason, you can't use a virulence
Right.
scale on something that's not a virus. If this is a protein, a misfolded protein.
But then why is certain species, why is the protein more virulent in that species when it's even from it's not from the other animal even.
Yeah. Yeah, or even within the individual.
The prion protein isn't from the donor. The prion protein from the very beginning when you transmit something is from the species.
Yeah.
What does that say? It says, of course you can use virulence.
Or this goes further when they tried to
I mean,
test.
even Collins admitted that by saying, well, people a VV at 102, is going to be much more susceptible. These are the people who've gotten BSE. So
There
BSE is more virulent for people who are VV. Now, there's another thing that nobody really wants to talk about, and they call familial and genetic. And I said years ago, I mean, I think, I wrote this sort of review, but I said it was the beginning of the BSE epidemic. And I was wrong probably about saying, well, it could be in a younger person. Maybe it's not necessarily, from the cows or whatever. I mean, I don't, what I said, it it wasn't wrong, but it was not, I would have phrased it
Sure,
differently
sure.
a year later. But basically, in that paper, I said the real prion diseases are the genetic prion diseases, like in the Libyan Jews. All of those people get a prion disease with abnormal prion, but it's not infectious. And they try to show, and Betty said, oh, well, it's infectious, but or Tatishi, it doesn't have the PRP res, it doesn't have the amyloid, and it didn't transmit serially. Okay. But these people, I asked the person in Israel who, I disagree with her about a lot of things, but she said, I take care of all these patients and I don't take care of them, but I see them and my husband's a neurologist. And all of these people, it's basically 100% genetic disease that's lethal, etc. And they say they transmitted one case of it, Tataishi,
Hmm.
okay, that Gadashek gave him, I think. Let me tell you what it looks like. It looks like sporadic CJD. It has that little tiny lesion in the mouse in the thalamus. I said, I don't know, you have sporadic CJD, but I can tell you that maybe FFI people can also get sporadic CJD. But that doesn't tell you that that's what most of them are dying from.
Mm-hmm. Okay.
Okay? You can have you can have CJD and Alzheimer's together.
Okay,
We
so
transmitted cases where people, that was CJD. We thought, oh, we're going to show Alzheimer's is transmissible.
yeah,
And guess what?
no.
It turned out to be CJD that they had. All the mice got CJD. All the hamsters got CJD. And then when they did the autopsy, these were biopsies. When they did the autopsy, guess what the person had? CJD and also some amyloid plaques because they were older.
Makes sense. Makes sense. Now, how do you, in your scope of things, there was a paper where they tried to develop a vaccine for CWD, and they gave it to a cervid. I think it was mule deer or elk. Might have been elk. It was elk. And what they actually did was they increased,
I think I told you.
they accelerated onset is what they did.
Right. So they made it against prion protein.
Explain.
Well, they made the antibody against prion protein thinking that they're gonna stop the virus or the agent from using prion protein or something.
They're swinging at the wrong ball. Yeah. Interesting.
Maybe it did something else. The prion protein, getting rid of the prion protein did something else. Just the way it did in Alzheimer's. It's supposed to be, oh, well, these people, they have a different amyloid. It's on the blood vessels that we're killing.
Okay. Well, hey, listen. It's 1:34. I know you have a 2 o'clock.
I know. I have to go.
This has been incredible.
It's been fun. It's
Thank
been
you.
fun.
Thank you so much.
If I talk as if I'm too definitive, just cut me off. I think
No.
I tend to be pretty careful about what I say.
You did great. It was perfect. I think that maybe we can hone in the future on a specific.
But I wanted to show some slides at the end because there is real data.
Yeah.
This is not a joke. And the fact that they never even quote the nucleic acid paper and they just keep repeating the same thing.
Which paper was that, by the way? I meant to ask you.
It's by, I can tell you, hold on.
Or can you send it to
I
me?
sent it to you, but
You did?
I sent it to you. I'll tell you where it is.
I have so many damn papers.
By the way, if you find something is off, like if you couldn't find the value of paper, whatever his name, the guy from Chile or from Spain, you can look. The best place to look is obviously PubMed is gone. They don't have my papers. I can't even find my old papers. That are in good journals like PNAS.
Sure.
They basically look on Google Scholar. You'll be able usually to find stuff, okay?
Yeah.
And that's what I use now all the time. So where is mine? Here we go.
The nucleic acid paper was.
Well, there's one on Sphinx, but this is the one. It's the first author is Batsios.
How do you spell that?
Botsios. Hold on, I'll tell you exactly the year. Nucleases. It's published in 2000, and the title is CJD and Scrapie Require Agent-Associated Nucleic Acids for Infection.
Require nucleic acids.
Require agent-associated nucleic acids for infection. It's 2 authors, Satiris, Botsios, and Laura Manuelidis. And it's in the Journal of Cellular Biochemistry, and it was, I suppose, published in 2016.
I know
and it
that.
has that graph.
I know that Manuelidis lady.
It has that graph. It has more graphs. It has a whole thing about how I did it. It has a whole bunch of things showing that as you incubate with time, the nucleic acid goes down, and so does the infectivity.
Okay, I will look that one closer.
It's not just one graph.
Do you think we could ever get Prusiner to come on with me?
Nope, nope. Listen, I will tell you a story. So Reed Wickner got hepped up about prions because he works on yeast, and he's going to get the Nobel Prize, he told me, because they're going to show the prions really exist in yeast, whereas Prusiner stuff, it's a totally different thing. But of course, they get money to do this because it's a prion, and prions are hot.
Sure.
So we're at Gold Spring. He goes to Cold Spring Harbor, and of course, I know Watson and Crick from 1978 when I gave my first nucleic acid.
You know
papers.
Crick and Watson?
Yeah. Yeah.
Or
So,
knew?
well, yeah, right, because Watson died. So Watson actually liked me, you know. So he said, I mean, Crick wanted to flirt, and his way of flirting is to say, I obviously presented some of my findings, you know, on nucleic acids, and they thought it was good. So he said, oh, there's another woman, another scientist, you know, who are totally useless. And women scientists we know can't be anybody's on the lunch line. That's typical Crick. But
Yeah.
anyhow, Watson was always actually very nice to me. So we had a meeting, on transmissible and stuff, and that's the first time Stan actually showed his gradients. It was before it was published of Bolton and Bentheim's band in a gradient, where they isolated this protein from and radio-labeled it. And I said, oh, that's great. I'm going to study that. That looks interesting. Everybody else said, poo-poo. I said, hey, it's the first thing we have that's only in the disease. It's not in the other. So it could be part of a virus. It could be, who knows? You know, it's definitely worth following. That's how I got into the early stuff, okay? So then a few years later, so in that meeting, Watson comes over and he begins to talk to me. Oh, Laura, how great to see you here, blah, blah, blah. Very charming to me. And Prusiner comes and he walks between us as we're talking.
Oh, wow.
And then he takes over the conversation. Finally, he says, oh, and Watson walked around to talk to me again, basically. It began. And then, because he had him cornered. He has all the important people cornered. That's all the Nobel Prize winners, like George Glenner and et cetera, who told me what he wrote is a piece of shit himself. He said, and he put me on, I'm on the paper, and he said, it never should be on the paper. It's a lie from the beginning to the end. So anyhow, he called me up. Okay. And so, actually, there's a picture from Cold Spring Harbor of me with George Glenner, speaking to him at one of the meetings that we had. Then, to me, Glenner and I speaking, at this meeting that we had what we had on transmissible. So then, he came to speak to me because he knew my work in nucleic acids, okay? And he knew that I was doing in situ labeling and all the stuff.
This is
that
Prusiner.
he began to get. No, this is Watson.
This is Watson.
So anyhow, so then Prusiner says to me, how do you know Watson? I said, yeah, well, I presented something at the 1978, big Watson Crick meeting in Cold Spring Harbor. Fine. So then this later time, there's going to be, Watson says, okay, he had this guy in yeast, who subsequently became a member of the National Academy of Sciences on the prion work in yeast. Okay. And Prusiner and Watson said, let's invite Laura. Wickner told me this story. And Prusiner immediately got angry and he said, if Laura comes, I'm not coming to the meeting. We're not having a meeting.
Sounds like a scientist who's confident in his ability to sell, if you will, or explain his science. Sounds like somebody who's not confident.
But listen, everything for him is selling. It's selling, or the press, the big thing, the self-importance, whole thing. Dick Laval said when he presented something, he summarized it. He said, so I see, so prion protein is insufficient to account for infectivity. So I thought that was great. I said, that's a very diplomatic way of saying it.
This is how Prusiner talks about, he says,
I know what he says.
In June, I sent it to Science, meaning his paper, his manuscript, with a letter reminding Abelson that he needed to exercise caution in his choice of reviewers, since the scrapie field was polarized and I had already accumulated a cadre of critics. So is that how peer-reviewed science works, is you get to pick the peers who review your science?
No, but I think it's fair for me to say I don't want Prusiner to review my paper. Okay, he didn't want me to review it. But the point is, it wasn't just me. It was a list of 12 or 15 people.
That's what
That's
it
a
sounds
very
like.
different thing.
Yeah, yeah.
Okay.
And then
So usually what people do is they're sort of aware. So they send it to, they say, well, give us some suggestions. These are and they'll give it to people who might disagree on the paper. Okay. And then they'll look at it. And sometimes they'll say, hey, it's a good paper, even though it's not what I
Yeah.
don't sort of agree with parts of it.
Sure.
It's well done. It's okay. If they're honest scientists, they'll say, it's a nice piece of work, but I don't agree with the basic thesis
I always
because
found
of
it
this
funny.
thing.
It says 3 reviewers. I don't know if you were a reviewer on this paper, this first paper or not, but
No, I wasn't. I was on the grant.
3 reviewers were reasonably positive. The 4th reviewer was not, and wrote a 3.5-page critique, which began, this is a mixture of fact, unproven hypothesis, and unconfirmed personal observations. Contains some relatively fresh, somewhat brilliant insights. Da, 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 da.
That would
Unfortunately,
not be me.
it
I
says,
wouldn't write.
unfortunately, the style is critically flawed and is finally more suitable for a statement of personal opinion, even
That's great.
prejudice, than the major blah blah. And it says the
So I
style
can tell you.
the
I can
style
tell you
is
what.
regrettably chauvinistic,
Right.
not adequately reporting the work of prior and current investigators. The main concept about
But that's
blah, blah,
great.
blah, blah. There's
That's great.
a bunch that matter. And the
So that
article,
that would
it says
that
the
would never
article
be
has
me.
a rather unpleasant, almost sarcastic tone, frequently belittling the work of others. Pretty
Right.
consistent.
Oh, that's what he did.
Yeah.
He said, "Who is Pat Mears? She's some technician."
Yeah.
Well, listen, Dick Johnson is one of the people who propelled Stan for the Nobel Prize, but he had a great thing to say about prions before Prusiner told him to shut up. He tells a little story about prions after the science paper comes out, and he says, "So there was this couple, and they wanted a child, and they only wanted a girl. They wanted a little girl." And he goes through the whole story, and they wait, and etc. And they told him, "Well, we don't think it's going to be a little girl. We think it's going to be a little boy." But they say, "No, it's going to be a girl. We know it's going to be a girl." And the baby's born, and they say it's a little boy. Oh, no, it's a little girl, and her name is Dorothy. So they named the little baby Dorothy, who's a little boy.
Hmm.
It's all in the name.
This is true.
And so basically, he wrote that. People knew it, and it was very funny.
And he
because
got in
Dick
trouble?
Johnson was intelligent.
He got
Oh,
yelled
yeah.
at for that?
Prusiner told him, don't ever say that again. But everybody who's older in the field knows this. And actually, Dick, all the neurologists wanted to have him have a Nobel Prize, and he got a lot of people in back of it. It was all political,
Okay.
And the whole story, Dr. Jekyll, Mr. Hyde,
Right,
come on.
right.
That's not science. It's one thing to say, look, if I were to say, what is the difference between replication of a virus and conversion? Conversion, you have a certain amount of something, and it still stays as the same amount, just a proportion of it becomes changed.
Mm-hmm.
But replication, you're making a lot more of yourself. It's
Sure,
very
sure,
different.
sure.
So, but I would say that. I would say, like a bacteria or something like this. You understand what
I'd like to thank everyone for watching this podcast in its entirety. My kids tell me that the younger generations have an attention span of about 5 seconds. I see that. I also see what's going on in our country. Video shorts have their place, but we've lost the art of deep dives that uncover the rest of the story, the facts, the context. As a junior in high school, I loved pursuing white-tailed deer, and I started falling in love with managing their habitats and their densities, enhancing them so that we could produce healthy does, high recruitment rates, balanced herds, and ultimately, really old, mature, rutting bucks. I'm committed to sniffing out fraud when it arises. The CWD scene sure does have a rotten stench. Most of all, I'm excited to hear your thoughts and your input on this and other episodes, so email me, jason@droptinepodcast.com. Good day.